Hello everyone, this is Dr. Raj Dandekar. I am very happy to share this video with all of you in which I'll show you how we rebuilt GPT-OSS completely from scratch. This is the truly open GPT-OSS, not just the open weights version. We have built two variations of GPT-OSS. One is the nano-GPT-OSS, which you can build under $10 on just one A40 GPU, but which still retains the essence of GPT-OSS. And the second is the entire 20 billion parameter GPT-OSS, which we have trained on the tiny stories data set. I'll show you the nuts and bolts of how we have built these repositories. In fact, the Nano GPT OSS repository which we have built, we compared it with GPT-2 and it beats GPT-2 on several performance benchmarks which we have tested. So this video is going to be a long deep dive on exactly how to build GPT-OSS from scratch, and it's again aligned with our mission of making AI truly accessible, not just open weights, but right from the dataset, tokenization, pre-training, everything. So I'm excited, and please share your comments in the description. Thanks. Hello everyone. Let's get started with this video. I'm very excited to be finally sharing this video with all of you. It's been something on my mind for a very long period of time that, okay, when companies release models and call them open source and everyone celebrates these models, they are not truly open source, right? We can call them open weights. So I essentially wanted to make a video by taking the open weights models from top companies like OpenAI, um, Quen, Gemma from Google, and then show you how to truly make it open, which means I want to pre-train entirely from scratch, starting from the dataset itself. So in this video, what we are going to do is that we are going to build GPT OSS, which is truly open source, which means we are going to replicate a nano version of the GPT OSS entirely from scratch, right from the dataset preparation to tokenization, assembling the model architecture, and then generating inference. The entire code base for this is made open source on our GitHub repository, Visuara AI. So you will see Nano GPT OSS. You can use this repository and do the entire pre-training yourself, as I'm going to showcase in this video. There is another repository which we have, which is called as truly open GPT OSS. So the reason we have named this repository as truly open is because this one actually has exactly the same number of parameters as GPT-OSS, 20 billion. And here we have built the 20 billion parameter fully from scratch. 20 billion parameter model entirely from scratch. For the purposes of this video, I am going to show you how to build a nano version of the GPT-OSS, which has reduced number of parameters, but which maintains the exact same architecture which they have used. Secondly, this nano version is so cool that it actually runs only on one GPU. You can use the A40 GPU, $0.4 per hour. And to replicate the results which I'm going to show you today, it will take you 20 hours on this GPU. So that's around $8 to $10. So what I'm essentially saying is that within $10, you can replicate the Nano GPT OSS entirely from scratch and even get inference results on the tiny stories dataset, which we are going to be using. So the title which I've given this video is how I pre-trained GPT OSS from scratch and how I got decent results. Now I don't want this video to be a very high overview video, which means I don't want to wrap it up in 10 minutes or 15 minutes. I want to show you every single thing which I did from scratch. And when I said I had a team of two people also with me, Aman and Naman. I'll mention their description when I release this on YouTube. But yeah, I want this video to be long enough so that you get a feel that you know all the different details of the architecture in detail, right? I will assume that you know something about transformers, let's say. You know something about attention. I will try to cover this as much as possible, but it will be good if you have some basic knowledge of, let's say, the attention mechanism. So my plan is to make this video around 2.5 to 3 hours. It can be longer or shorter than that. I am sitting with a cup of coffee, as you can see, anticipating that the video will go on for a longer period of time. But the whole aim is essentially to move towards a truly open source system, right? Where I want to teach you how you can build truly open source models entirely from scratch. And it's a wonderful exercise to actually see what they have built and try to use it. So this is GPT-OSS, which was introduced 1 month back, and it was the second open source model by OpenAI. Their first open source model was the GPT-2, which was this paper, Language Models Are Unsupervised Multitask Learners. After which point, Andrei Karpathy made a nano-GPT, which was truly open source, starting right from the dataset itself. OpenAI took around 5 years to release their next open source model, which we are covering today, GPT-OSS. And this created quite a storm because uh, all of their models which came in between, GPT-3, 3.5, 4, 4.0, were all closed source, right? GPT-OSS was one of their first transitions towards the open source movement. So I was very excited by it. And naturally, it took me around 2 to 3 weeks to come up with the lecture notes to make this video, which have now become quite comprehensive. And now I think I'm finally ready to share it with all of you. So just like what Karpathy made for Nano GPT, the goal is to, of course, make a Nano GPT OSS. Uh, Andre Karpathy is my inspiration. So even if I get to 15% or 20% of whatever he achieved with Nano GPT, I would consider this repository to be a success. Okay, so with that in mind, let's get started. Uh, the way we are going to divide this lecture is going to be in 6 steps. We'll start with the data set, we'll start with tokenization and creating input output pairs. So, all these 3 steps come under the data pre-processing block. If you already know how data pre-processing is done, you can directly jump towards step number 4 of this video, where we are going to go into detail about every single aspect of their architecture, including attention sinks, grouped query attention, uh, rotary positional encodings, RMS normalization, then their feed forward neural network, the CLU activation, mixture of experts, etc. We'll go through this all. Please keep in mind that they had two versions, the 20 billion and 120 billion. So mostly I'll be talking about the 20 billion, but the 120 billion just seems to be a scaled up version of the 20 billion model. For example, in the 20 billion, they used 24 attention blocks, whereas in the 120 billion, they used 36 attention blocks. The 20 billion, they used 32 experts, and in 120 billion, they used 128 experts. And 4 experts were active per token. That remains the same across 20 billion and 120 billion as well. The vocabulary size for this model is 201088. I'll also explain to you about the tokenizer which they used and why it's a bit different than the other tokenizers which came before it. The embedding dimension they used is 2880, 4 experts activated per token, and the maximum context length supported is 131,000. Still a lot lower than Gemini's 1 million context length. So all of this will be covered in the GPT OSS architecture, and this remains the core backbone of this lecture. After the architecture is assembled, we will spend time with respect to pre-training in step number 5. We'll set up the pre-training pipeline and we'll run the pre-training. And in step number 6, we are going to do inference, right? So I'm going to be referring to this repository whenever I'm going to explain the pre-training setup to you. I wanted to do this entirely on a Google Colab, like usually I do for all my videos. But I think that for this particular architecture, it's just better to split it into different folders. So when we are going to train, I'm going to show you this file, which is training.py and trainer.py essentially. And when we are going to do inference, I'll refer to the inference.py. All right, so this is going to be the main skeleton or the architecture of today's lecture. And as I mentioned, you'll just need $10 to $15 to replicate what we are doing here. So the entire repository is, I'll make it public, and you just have to go to run pod, click on deploy a pod, and you can link a GitHub repository and start with the A40. If you want the training to proceed quickly, the training will happen 5 to 10 times quicker on a H200. So you can potentially finish the training within 2 hours on an H200, but on A40, it takes 8 hours to run one epoch. Um, all right, everyone. So let's dive into the video and let's start into the different steps. All right. So let's get started with the data set first. Now, this first step, which is taking the data set, then tokenizing the data set, and then passing to a model, that step is completely missing from open weights models. So when OpenAI released their GitHub repository for GPT-OSS, there was no mention regarding the dataset which they actually used. There was no mention regarding how the tokenization was done. Of course, they have released their tokenizer, but they did not show how they applied that tokenizer to the dataset. So the challenge when we wanted to create this GPT-OSS from scratch was to choose a dataset wisely so that our model should be able to generate inference. That is number one. So we need to check whether the model is working or not. And that check will only happen if the model generates coherent text. So the data should be large enough where some things about a language need to be taught to the model so that the model can learn the language on its own. That is number one. And the second is it should not be too large that people are not able to replicate this within the budget of $10 to $15 which we have. And we found a dataset at the intersection of these two things, right? And that dataset is called as the tiny stories dataset. Essentially, this dataset is based on the paper which is called as Tiny Stories: How Small Can Language Models Be and Still Speak Coherent English. What the authors showcased here is that if you smartly construct a dataset which preserves the nuances of English language, which preserves the structure, the meaning of English language, even if that dataset is small, let's say you create a small dataset like this, you don't need a billion parameter model to learn about the language from that dataset. Even models as low as 1 million parameters, 10 million parameters, 15 million parameters can learn the form and meaning of English language through this dataset. So the authors thought about this question: how can we construct such a dataset which preserves or which contains the key elements of an English language, but not too many unnecessary things? So that's when they came up with tiny stories, right? It's a synthetic data set of short stories that only contain words which typical 3 to 4 year olds can understand. The beauty of this data set is that it does not contain too many unnecessary complex information, but still it will have enough stuff which captures the nuances of English language. Because let's say in an English language, Mary kicked the ball, subject, verb, and object, right? That syntax will still be preserved when we are considering a story for a 3 to 4 year old kid. So there are a lot of patterns for the model to learn, right? So they created such a tiny stories data set. Let me show you one such story, how it looks like. Uh, yeah, let's say this can be one such story. Once upon a time, in an ancient house, there lived a girl named Lily. She loved to decorate her room with pretty things, etc. Let's say this is one such story. What they did is they created a data set which 2 million such stories. So if you take a look at this data set, every single row of this data set was one such story which a 3 to 4 year old kid can understand. And they asked the question that, hey, with this data set, how small can my language model be and still be able to generate good stories during inference? So essentially, they wanted to push the limit to how small we can go and still have the language model understand the form and meaning of English language. And yeah, they wanted to understand how small can we go, and still the language model needs to understand the form and meaning of English language and be able to produce coherent stories of its own. So the real test of whether our model has worked or not is if it's able to produce new stories during inference time, right? And they found that even models with the size of, let's say, um, 1 million, and so this is a text generated by a 1 million model. What are you doing here? Lucy smiled and said, I'm going to help. The ranger smiled and said, that's a great idea. The model has learnt about the format of the English language and the meaning, right? That's incredible. With even just 1 million parameters. So then we thought that, okay, let's take this data set itself. Let's take this data set, which is 2 million stories. And that's good enough for a small model to learn about English language. So let's test out our nano-gpt-oss architecture on this dataset. Ideally, what GPT-OSS would have done is that, of course, they would have collected data from all over the internet, right? Uh, they would have collected data from all over the internet, and they would have then trained their model on huge billions and trillions of tokens. Now, as I'm making this video, we are working on one more dataset, which is Hugging Face Fine Web Data, which is a refined collection of web data. And it's still huge. It's 25 billion rows, right? So it's around 10,000 times larger than the tiny stories dataset. But now that we know that the nano GPT works on the tiny stories, we can easily scale it for the fine web dataset. I'll release a separate video or add a separate augmentation to our GitHub repository once we finish training on this dataset. Right? So I hope all of you actually understood what's the data set which we are using here. We are going to use 2 million stories in this tiny stories data set, and we are going to pre-train our model on that data. Remember, the model has no clue about the form of the English language like subject, verb, object, nothing. It has no clue about meaning. So for example, what do I mean by meaning? Let's say consider this sentence, right? Blue electrons eat fish. Now, this sentence, the form of this sentence is correct. Subject, verb, object. But no language model should generate this text, right? Because it does not carry any meaning at all. So during inference, our model should not only maintain the form, but it should also maintain the meaning of language. It should not construct stories which look like this. So the real test for us will be during inference. When we reach step number 6, we will again evaluate the kind of stories which our model is generating. All right. So this is with respect to data sets. Our first step is now done. In the second step, what we are going to do is that we are going to tokenize the data. So remember that language models or any AI for that matter cannot really understand words, cannot really understand English language like we do. So we need to break down the words into numerical format. So let's do an interactive exercise together, right? Let's say I take a story such as this. I've taken a screenshot here, and I've brought this story over here. Now, what you want to ideally do is that you want to maintain a vocabulary I'll tell you, so this is point A. I want to go to point B where we have maintained a vocabulary. Think of it like an encyclopedia. That vocabulary has token IDs 1, 2, 3, dot, 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 up till 200,000, let's say. And every ID corresponds to a word. Like, let's say this is one, day, the, and let's say this is umbrella. So what will happen is that when this story is passed to our model, actually this story won't be passed. What will happen is we'll look at, so let's say one, it belongs to the vocabulary, right? And it has token ID number one. So it will be assigned one. Then we'll look at day, it has token ID number two. Then we'll look at, let's say little, maybe that has token ID number 5000, right? So similarly, when we look at each story, every single building block of that story will be converted into a numerical format, and then those bunch of numbers will be passed to the model. So the idea is that as a human, I'm sure all of you see a story here when I show this, right? But when we are done with the tokenization step, the model will not see a story. The model will see a list of numbers which is being passed to it. The question is that how do we go from point A to point B? How do we create this vocabulary? So soon you will realize that the first step you need to do on your journey of going to from point A to point B is that how do you want to break down your text? I mentioned building blocks of the text, right? How do you break down the text? So once I break down my text, I can assign a token ID to each building block, and then I can create a vocabulary like this, right? So how do I break down this text? The simplest way to break down the text is words, right? So you assemble all of the stories, right? You break it down into words. So for example, in this story, we have these words, one, day, little, whatever. And then you assemble all the list of words. And then from this, you get a list of unique words. You get a list of unique words, and then you arrange them in alphabetical order, and then you assign token IDs. That's a vocabulary, right? So this process of breaking down text into building blocks is called as tokenization. And the type of tokenization which I just explained to you over here, that's word-based tokenization. Where essentially what is done is that before even tokenizing our text, first some other piece of text is taken, some other data set is taken. This is some data set which maybe consists of many words in the English language. Or if we are dealing with a multilingual model, it will consider data sets of multiple languages. We will assemble all the words together, unique words, and then we'll create a vocabulary. And once this vocabulary is created, we'll apply this vocabulary on our specific data set, which is the tiny stories, and then assign a number to each word. What's the major issue with this approach? You can pause the video and think about this. If you have been through my previous videos, you know I like to ask this question. The first major issue with this approach is something which is called as the out of vocabulary problem. Now remember that whatever data set we are considering here, there can be spelling mistakes when you are dealing with real life data. So let's say there is some word with STRIs. This does not mean anything, right? Ideally, it should be stories. But let's say if something has been written like this. So what will happen during tokenization is that we will look at this word and then we'll try to find a mapping for this word. And we'll see that there is no such mapping because of course such a word does not belong in the English language at all. So if you have taken a lot of words in the English language and created a vocabulary out of it, this word does not belong there. So then there is no token ID assigned to this word. That's called as the out of vocabulary problem, which is bad for us. Then the language model will not know what to do with this word. The second issue is that consider words like run, running, runner. So all of these words will be assigned a different token ID, right? But clearly they have some root. but that entire meaning is lost. All of these will be assigned different token IDs. So there is no prefix meaning which is retained. That prefix meaning is lost, the suffix meaning is lost, not very efficient. Another issue is that if you take a look, if you go to Chat GPT and I just ask approximate the number of words in English language. So it's more than 1 million words if you add all of these, or if you consider all the combinations. English language itself has more than 1 million words. So think about your vocabulary size here. It will be 1 million, that too for English language. If you are building a multilingual model, it might be 2 million, 5 million. Having such a large vocabulary size is not good for designing language models. Why? Because it really blows up the number of parameters you require for your training. The more your vocabulary size, the more the number of trainable parameters, the more your computational cost. So even if you take a look at GPT-OSS, right? GPT-OSS used a vocabulary size of 201088, which is still way less than 1 million. It's about 5 times lesser. It's already a bit on the higher side. So vocabulary size plays a very important role. And if we use word-based tokenization, the vocabulary size shoots up. So we cannot do that. What is another way of tokenization? So this is word-based tokenization. That's fine. Another way of tokenization someone can say is that forget about all this. I'll give a simple way. You just maintain a vocabulary of 26 characters and assign 1, 2, 3, 26. And then what you do is that simply you break your text into characters and then assign numbers to characters accordingly. That is still tokenization. And the vocabulary size here is 26. So it really solves my issue of the vocabulary size being too large in word based tokenization. So, what's the issue over here? Uh, the issue over here is that, first of all, we destroy the essence of English language. The moment we use character level tokenization, so this run and runner, right? It's broken into R, U, and N. The essence of language is lost. Uh, the moment words are broken down into characters, there is no language essentially, right? You're looking at individual characters. The meaning comes when characters assemble together and form words. That's what we want to exploit in the language model. Why did convolutional neural networks become so popular? Think about it, right? Why did CNNs become so popular? Because they exploited properties of an image. They exploited the property that two pixels of an image will generally lie closer to each other. They exploited the property that these kind of filters can capture features in an image when they slide over the image. That's why CNNs work. So CNNs work because they exploit the property of the data set, which is images. Here also, if we want language models to work, we need to capture the properties of the dataset, which is text. And what's the property of text? Words carry meaning. So the moment you break down a word into characters, that entire meaning is lost, which is not good, right? That's one major issue with character level tokenization. Another issue with character level tokenization is that, well, it's something which is related to the context window of a language model. Now, the moment you do character level tokenization, let's say you have text like this, right? When you do character level tokenization, the issue is that it will get converted into so many different characters when you tokenize it that you might exceed the context window of an LLM, right? So, context window is the amount of information the LLM can pay attention to at once. So, if the number of tokens in our story become more than the context window, the LLM can only pay attention to to this much information. All the information which I am now marking in red is completely lost. So our model predictions will be much worse. That's why people don't use character level tokenization. It has two major issues. The first is that it destroys the It destroys the essence of English language. Words carry meaning when grouped together. The second is that it has this context window issues where the number of tokens just becomes so large that they exceed the context window, and hence there is a lot of lost information, which is not good when you are designing a language model. So character level tokenization has its issues. Word level tokenization has its issues. We saw the out of vocabulary issue. We saw the large vocabulary issue, which is computationally expensive. So then what's the best of both worlds? The best of both worlds is to use a subword tokenization scheme. What it does is that it says that why don't we use the advantages of both these? What's the advantage of character level tokenization? We'll never have the out of vocabulary problem, right? Because everything can be broken down into characters, no matter if it's misspelled. So in subword tokenization, we start with characters. That all of those are added to the vocabulary by default. So we will never have the out of vocabulary issue, right? So the out of vocabulary issue is solved. Then secondly, what it does is that instead of taking all the words in the English language, like we are seeing here, instead of taking all the words in the English language in the vocabulary, it does not do that. Instead, we do something clever. What we do is that when you look at a piece of text, you merge frequently occurring characters together and you retain them as subwords. For example, this word ization can come across in many words, right? It can come in tokenization, it can come in modernization. So this ization is now a subword because it's a bunch of characters which frequently occur together. So we don't want everything to be, so token and tokenization don't need to be separate tokens. Token can be one token, ization can be one token, modern can be one token, ization can be a separate token. So that way this prefix and suffix issue which we saw over here, right? Let's say this run, running and runner. Now run will be a separate token because it's very frequently occurring. ing can be its own token, etc. So in subword tokenization, instead of having every single word as part of the vocabulary, we merge frequently occurring characters and as subwords, and then they are stored. Words which are very unique, they will still be retained as individual words, right? Which are not used very often. So we have characters, we have frequently occurring subwords, and then we have rarely occurring infrequent words. All of these will be in our vocabulary. So since every single word is not a token, our vocabulary size won't be huge. So it solves that computationally expensive issue. So it solves actually both of the issues with word-based tokenization, and it also solves issues of character tokenization of destroying the essence, because we do have words and subwords as tokens, and it solves the context window issue also, since not everything will be broken down at a character level. Words and subwords are still tokens. So subword tokenization gives us the best of both worlds. This algorithm which I told you, which merges frequently occurring characters at subwords, that's called as the byte pair encoding algorithm. So usually what providers like GPT-OSS actually do is that they first start with some data set. And this is different than the pre-training data set. This is the data set for tokenization. And people rarely talk about this because it's not that cool, right? Uh, Pre-training is cool, inference is cool, but no one talks about tokenization. I believe there is a lot of scope for research in this field. So you start with the dataset for tokenization, like GPT-OSS would have done this. Then they apply a byte pair encoding algorithm on this, and then they get their final vocabulary, which happens to be of the size of let's see what it was, 201088, which happens to be of the size, final vocabulary size is 201088. So now you must be thinking, how does this add up to 201088? You have to define a length at which you have to stop. So the merges will continue happening until you reach the vocabulary length. Now for a long time, OpenAI has been open sourcing its tokenization schemes, right? So if they have defined any specific merging rules, etc., it's all open source. And you can play around with this if you go to Tick Tokenizer a bit. So Tick Tokenizer is an app where you can actually check. So this is GPT. GPT-2 Tokenizer would also be here. At least it was there last time I checked. Yeah, this GPT-2 tokenizer. We also have GPT-4 tokenizer, 4.0 tokenizer, and um, let's see what else. This O200K base. So this is what GPT-OSS started with. They augmented it later with something called Harmony. So let's see actually. You click on O200 base and then let's just type something over here. Let's just take uh, something from our text and let's type it over here, right? Maybe I'll go to some movie which I like, and what I'll do is that I'll take the introduction and I'll put it. I'll show you how it's essentially tokenized so that you understand tokenization, right? This what I'm showing right now will exactly what will happen to our stories when they are tokenized using the GPT-OSS tokenizer. So you put this story over here, and here you see what are the different tokens. So Whiplash, if you see this is what I meant by subword tokenization. WH is one token, IPL is one token, and ASH is one token. So this word is broken down into three subwords. Why would this be done? Because ASH, IPL, and WH would be commonly occurring bytes together, and so they become one token. Whereas American is one full token, that's a full word. Psychological is one full word. In Teller, T is one word, and Eller is another word. So this is character, this is a subword, and this is a full word. That's why it's called subword tokenization, right? So this one piece of text will be broken down into 515 tokens. If I now do it for my simple story, let's see. So if I take this story and if I use their tokenizer, it will be broken down into uh, just a minute. Yeah, I should do this. Yeah, it will be broken down into 158 tokens. So one day, a little girl named. So all of these seem to be separate words, but Lily is L and ILY, right? Uh, but even small changes lead to different tokens. The moment you have an apostrophe here, Lily becomes one full token, right? But here, Lily becomes L and ILY. Actually, here Lily and this space is one token. So the moment there is a space here, this whole thing becomes a token. So let me actually, so this Lily, it does not have a space before it, but let me try to add a space there now. Yeah, see, the moment I add a space, it becomes a full token. And the moment I remove that space, it's broken down into two tokens. So those are the merging rules. And then you can get full words as token or subwords as token. This is the tokenization scheme which we are going to use. Okay. But this O200K base, that's not what GPT-OS is used. They went one step further than that, and they actually released something which is called as Harmony. So it's called as O200K Harmony. So O200K base is what we saw. O200K Harmony is one step after this point, right? So what this Harmony tokenizer actually did is it's still based on byte pair encoding. That's fine, but it added two new features to the encoding scheme. It added special tokens for chat formatting and for role-based prompting. Essentially, this data set which I mentioned to you, right? This data set for tokenization. If you have conversations in that data set, you can add some special tokens there. Special tokens such as, let me show you. So if you go to, yeah, so these are some special tokens. So if there is a text in your data set or a conversation, you can add this start of text, etc. So these are chat tokens, they called it. They added some chat tokens so that you can indicate when a chat is starting, right? Um, yeah, they, so for example, here they added something like start, end, message, etc. So that the model actually, when it's pre-trained, it knows when chat conversations are happening. They also added some uh, roles actually. So they added multiple roles you can add. So earlier, these roles were not added in the tokenizer itself, but with Harmony, they added these roles in the tokenizer. So when you're designing, or actually when you are doing the pre-training, uh, In the pre-training dataset, you can add those tokens so that the model can learn. Earlier, I mentioned that you can add those tokens in the dataset, but in the dataset for tokenization, you don't need to add those special tokens. Once you have the vocabulary will have the special tokens like start of message, end of message, etc. And then when you are actually taking your dataset from the whole web for your pre-training, that dataset you can add these tokens so that the pre-trained model itself knows what a chat conversation looks like, etc. So that for downstream tasks, things just get a bit easier. So I actually was interacting with Chat GPT about uh, in your pre-training, how do we make the maximum use of this new tokenizer during pre-training? So if the corpus is just plain text, we don't need to add the start, end message or role tokens, which Harmony provides. So if our text is very simple, we don't need to add these tokens, and then Harmony will tokenize the text as efficiently as O200K base. So for purposes of this video, we won't be needing these tokens because all of our text is just simple text. It's not in a conversation format or anything like that. But if our corpus includes dialogue or chat data, we should encode it with special tags like start. So this is the role, right? So these are the messages start and end, and these are the roles like system, user, etc. So Harmony added these role tokens also, which usually were not there in the tokenization. This teaches the model an explicit role and turn structure instead of just guessing from user, assistant, etc. So earlier people just dumped the entire chat and the model had to guess who is the user, or there are two people talking, etc. When does the chat start? Uh, who is asking the questions, who is replying, etc. But all of that now can be encoded in your pre-training dataset also. So remember, this is of course more work before pre-training, but it will lead to a better model. If you want to do tool calling function execution downstream, you can ideally include call or constraint in your pre-training or fine-tuning data, or the model won't learn naturally how to use them. So I think the reason why these things are added is because slowly things are going towards agentic tool usage, right? So it just turns out that maybe the model does better at agentic capabilities when you add these tokens in your pre-training data set as well. Or maybe the model does better at reasoning when you add these. So if you see for agentic models, tool use or reasoning, we can start including channels like, so it has three channels: analysis, commentary, and actually one more channel is there. Three message channels: analysis, commentary, and final. So commentary is for when we are generating tool calls. Analysis is for when generating chain of thought reasoning. And final is for generating end user. So let me actually now go to Chat GPT and ask, can you give an example of how I can use these, what are they called, message channels while pre-training, let's say. The core idea is to let the model separate different streams of reasoning. Final is what the user actually sees. Analysis is reasoning steps, and commentary is what tools are used, etc. Let's say user asked a math problem with harmony tags, and the model structured response is this. So the analysis channel contains the chain of thought, while the final channel contains only the clean answer. Right. So the chain of thought is into the analysis channel, whereas the final channel only contains the clean answer. That is how the response will be given through this model. Earlier, it did not happen like this. Even if you want to make a tool call, right, the model response will now mention what it used, like the channel which is it used is commentary, because now it's doing a tool call in the background, let's say. Yeah. So if you're in pre-training, if the data set is in plain text, we just train on final. If we want the model to think during pre-training, we can inject analysis tags in the data set itself while pre-training. And if you want to inject agentic capabilities, we can inject the commentary, tool calls, and planning steps in the pre-training dataset as well. I believe that GPT-OSS added these in the pre-training dataset so that the model can learn to reason and the model can develop agentic capabilities as well. But we are not going to do that. I thought it will be just important to share this with all of you in this step, step number 2, which is data tokenization. So at the end of this step, what we have done is that we have taken our data set, right? We have taken these bunch of stories. We have used their Harmony tokenizer, which I just showed you over here, which is based on the O200K base, right? Which we just saw here, the O200K base. It will tokenize every story into individual tokens like this. And if any special token is there, it will add these numbers to that special token, right? So if you are thinking, how does the vocabulary size have this 201088? So this number is because of the special tokens which are added on top of the 200K. So in the code, what is actually done is that uh, we take each individual story and it's broken into token IDs like this. Like you saw over here, each individual story is broken into token IDs. And then what we do is that we store all of those token IDs on disk. We don't store it in RAM. The reason we store it in disk is because it just becomes much faster to access it if we store it on disk rather than if it's stored on RAM. I tried disk storage also, but the thing is, uh, I tried RAM storage, but it's very slow first of all, and data loading just becomes faster if you're saving the tokens onto your disk, and then it avoids RAM overload. We don't need to retokenize. Uh, we can reuse the .bin for multiple training. So there is a, you will have, after you do the tokenization, you will essentially have two files. You will have the train.bin file and you will have the validation.bin file. So imagine, now stay with me on this thought. Imagine all of these stories. Every single story is converted into token IDs. All the token IDs of all stories are brought together. They are written onto the disk, right? And then they're broken down into two files. Train.bin, let's say, has 80% of that. Validation.bin has 20% of that. So after this tokenization stage, you are left with two bags. One bag consists of training token IDs and validation. The second bag consists of validation token IDs. That's it. And both of these bags are stored on disk. These bags are not stored on the RAM. So the way they are stored on disk is that we break the whole data set into batches and we write each batch individually onto the disk. So batch 1 is written onto the disk, batch 2 is written onto the disk. Similarly, the last batch is written onto the disk. Now we have the entire thing, all of the batches onto the disk, right? And then you split into two parts. Train.bin gets 80% of it, validation.bin gets 20% of it. That's it. So imagine you are a language model, right? Life is so hard for you. You just have a huge bunch of collections in train.bin. You have a huge bunch of numbers in validation.bin. And you have to make out, you have to understand the structure and meaning of language from this bunch of random numbers which are now thrown at you. And remember, you had 2 million stories, right? And if you assume that one story has 100 tokens, you essentially have 200 million tokens. So this would be around 150 million tokens, and this would be around 50 million tokens. As a language model, life is hard for you. You have to then look at this training bin, you have to look at these tokens, you have to make sense out of it. You have to understand that subject followed by verb followed by object is the correct grammatical structure. You have to understand that I cannot print things like blue electrons eat fish, etc., right? So this is the end of the second step. If you go to the code right now, you will see that yeah, we will eventually get to the trainer.py, but before that there is this data loader.py. And in the data loader.py, we are doing exactly what I just mentioned to you. What we are doing is that first we load the data set. Okay. First we load the data set and then we are using the tokenizer. What this tokenizer does is that it gets the Harmony O200K and it breaks down every story into a bunch of tokens like this. Until this step, we have taken our stories and broken down into tokens. Now, but we have still not essentially written them uh, to the disk or anything, or we have not yet created input output pairs from these tokens. You have two options after this particular point before we create input output pairs. So after this point, you can write it to the disk, or you can just essentially keep it like that in the RAM itself. Things will be a bit slower like that, but you can do it and then check what works the best for you. And once we have created the train.bin and the validation.bin, right? And in this code, I'm just showing you a very simple thing where we have created the train tokens, and we have created the validation tokens, right? I have not I have not written the code of creating the bin files and storing it into the disk, but it's just a bit faster. Here I have just shown it in a simple manner so that none of you get confused, right? So think about, until this point, we have a huge bag with training tokens, huge bag with validation tokens. The next step which we have to do is creating the input and output pairs. The reason it's very important for all of you to understand is that in many other machine learning tasks, input and output is clearly defined, right? When you want to do a brain tumor classification, you have an image, you want to classify whether tumor exists or not, input, output. When you want to predict the price of a house, the input might be number of bedrooms, square feet, and the output is the price. But how do you create input and output for a language model? That's what we are going to see in the next step, right? So let's move to that now. So in the next step, what we are going to do is that we are going to learn exactly how the input and the target pairs are created by a language model. And there is a reason why I say created by a language model and not for the language model, because the language model actually creates the output pair, output itself, once it gets the input. So the way it's done is as follows. Imagine that you have collected a bunch of data. If you are building GPT-OSS, you have tokenized the data, you have training.bin and validation.bin. For now, let's just look at train.bin. It's just a bunch of token IDs right now. It has no structure, there is no input, there is no output. You have to take those bunch of token IDs and convert them into input and output pairs, right? So that we can then train our model and then define a loss function between the true output and our model prediction, and then we can try to reduce the loss as much as possible and try to optimize our model. That's going to be the whole idea. So the way input output pair is created is that, let's say if you have a paragraph such as this, there are two things which you need to define first. The first thing you need to define is something called as the batch size, and the second thing you need to define is context size. Remember when we talked about the context window when discussing about the limitations of character tokenization? This is where it comes into the picture. So let's say you have defined the context window to be 4 tokens. So my model can look at 4 tokens at once. Here is how you create the input and target pair. So the first input pair will have only 4 tokens. Why? Because we have put the context size to be equal to 4. So it can only look at 4 tokens at once. Right? Or let's say for to match this demonstration, if the context size is equal to 5, then the model can look at 5 tokens at once. The strangers seem to be 5 tokens at once. That's my first input. So the 5 token IDs corresponding 1, 342, 534, 35, and 98. That's my first input. How do I get these token IDs? We have already seen that you put this, you take this, and then you use your tokenizer essentially. We have already tokenized, but here I'm just showing it for reference. The stranger seem to be the 5 tokens, and these are the 5 token IDs corresponding to it. Okay. So these are the 5 token IDs. Then how do we generate the output? Here's the key part. So the LLM generates its own output by shifting the input to the right hand side by 1. So what it will do is that, okay, this is my input. I'll shift the input to the right by 1. So then my output becomes this. So my output becomes stranger seemed to be angry. So out of these four words are common. So if you look at the output pair now, the output pair, it starts from 342, stranger. So 342, 534, 35 and 98. These are the same. And just one more is added, which is angry, which is 11 now. So this is my first input and this is my first target. So you might be thinking, why is the input shifted to the right by 1, right? So think about this. The stranger seemed to be. This is my input. And remember that a language model, what a language model is that it's an engine which predicts my next token. A language model is only pre-trained to predict the next token. So we want to teach the model that when the is the input, stranger is the output. That's why in the output, the first is called the. The first is stranger, which is 342. And that's the reason the output is shifted to the right by 1. Then this stranger is again added to my input. So if the stranger is my input, then what's my output? Then my output is seemed. If the stranger seemed is my input, what's my output? 2. If the stranger seemed to, what's my output? That's B. And if the stranger seemed to be is my input, then my output is angry. You see, so this input and output pair, it looks like one input output pair, right? But there are 5 input output prediction tasks which are happening here. First task, second task, third task, fourth task, and fifth task. There are 5 input output prediction tasks which are happening. And all are geared to make sure the model can predict the next token correctly. That's why the output sequence is the input sequence shifted to the right hand side by 1. That's the first variable here, context size. But where does the second variable, batch size, come into the picture? It's to decide how many input sequences you need in one batch. So here I have 4 input sequences in one batch. That's why there are 4 rows here. So 4 rows in the input, 4 rows in the output. So what will happen is that this entire input, which I have marked over here, let me let me copy this. This entire input which I have marked, this input will essentially go through my model and the model will give me some predictions. Let's say the model gives me some predictions, right? All of these predictions will be compared to my ground truth, which is this output. All of these predictions will be compared with this output. So these are the model predictions and this is the output. This is the ground truth. So let me call ground truth. And then based on the prediction and the ground truth, I'll get my loss. Right? Once I get the loss, I can do a back propagation and update my parameters. So once one entire batch is processed, I will get the loss, I will update my parameters. Then I will process a second batch. How do I get the second batch? I look at any other 4 input sequences like this and create the output sequences. So such kind of a pre-training task for language modeling, it's actually, there are 2 terminologies for it. First is called self-supervised learning. Why? Because the model creates its own output by shifting the input to the right. That's why it's self-supervised. And it's also called auto-regressive. Auto-regressive means the output, this is the first output, it's then added to the input again. So the stranger is the second input and then seemed is the output. Then seemed is again added to the input. So the stranger seemed is the input, 2 is the output. So it's called as self-supervised and auto-regressive. I hope you understand these terminologies now. This thing which I just explained to you right now, it's called as the next token prediction task. We are creating the inputs and the outputs are shifted to the right because we want to teach the model to predict the next token. That's one incredible thing which I've consistently found about language modeling. We are just teaching the model to predict the next token. But isn't it amazing that through this next token prediction, the model seems to understand the form and the meaning of the language itself? That's incredible, I think. So now I hope you visualize the framework, right? All of these token IDs which are there in your bag. Now you have a framework to create the input and output pairs. You have the context size. So you select one input sequence randomly, you select the output. If batch size is 4, you select four such, you give the batch to the model. The model gets the loss, you update the parameters. Then you get another 4 input sequences, you get the loss, model updates parameters. So it's like pulling out important information from this bag, updating the loss, then taking another information from this bag, etc. So if you look at the code now in the data loader.py, you'll see something very interesting here. So essentially what you're doing is that you get the input chunk and you get the target chunk. So the target is just the input which is shifted to the right hand side by one. That's it. And you will see that here we have also mentioned something called as stride. What stride essentially means is that if, let's say, if I get my first input, if I get my first input sequence as this red, uh, if I get my first input sequence as the stranger seem to be, my second input sequence should ideally start over here, right? I don't want an overlap between my second input sequence and my first input sequence because I'm already covering these words in the first input sequence. So my second input sequence should ideally be here. That's called stride. So so to get my second input sequence, I skipped the number of tokens equal to the context size, right? So that's stride. So essentially taking those steps to get my next input. So usually to have inputs which are separated like this, but still they cover the whole training data, you need the stride to be equal to the context length. And that's what you'll see in the code here. If you see, uh, GPT-OSS used a context length of maximum context length of 131k tokens because they have huge amount of data. For us to simplify the training process in nano-GPT, we have used a context length of 4000. So here if you see, the max length and stride by default are 8192, but when you actually create the training input data and output data, you essentially put the max length to be equal to context length, which is 4000. So you remember I mentioned two parameters. The first, the context length, so which is the max length, that's going to be 4000. The second is the batch size. So the batch size is going to be 5 over here. We are looking at 5 input sequences at one time. So you get the input chunk and then you shift the input chunk to the right by one. See, uh, right. So that's all we are doing actually over here. We get the input, we get the input sequence, and then we shift the input sequence to the right hand side by one. And then we have to mention how many do we need in one batch. That's specified with the batch size. So I hope all of you understood what's going on here. We get the training and the validation tokens in those two bags. Then what we do is that we go through my tokens and I need to first define my context length, which I'm using 4000 here. So in one input sequence, I have 4000 tokens. Then I shift to the right by once and I get the output sequence. I also use the stride, which is equal to my context length, so that there is no overlap between two input sequences. So I get the input and target this way. And how many will be there in one batch? Once we have to define a data loader for the training and validation data set. So every time you want to calculate the loss function, the data loader will supply you with one batch. You get the loss, you update the parameter, then the data loader will give you the next batch. So you remember I mentioned to you, it's just like taking things from this bag whenever you want to compute the loss. The more formal way of doing it is to use data loaders from PyTorch. That's the more formal way of actually going about it. But we are doing the same thing. We are getting the For one batch, we are getting the input sequences as prescribed by the batch length, shifting to the right by one, getting the output sequence, passing the input through the model architecture, getting the predictions, then um, computing the loss between the predictions and the ground truth, and then doing the back propagation. So in this step, data loader.py, it actually seems like a small code. I think it's only about 40 to 50 lines of code, right? But here we have done multiple things. We have loaded the dataset, we have tokenized the dataset, and we have created input and output pairs for the training data and the validation data. It's this part until here, it's what is not covered in open weights libraries. So people have no clue about how to operate in this part. Normally, when you directly see this repository, it feels very confusing. What do I do after this point? If I want to build GPT-OSS from scratch, how do I exactly do that? There is no way or no blueprint to do that, right? I hope this lecture serves as that blueprint. Now, once our input and target pairs are created, we now move towards the most important part of the lecture, which is the GPT-OSS architecture. So let's now start understanding the brain of GPT-OSS, and let's build all the blocks which makes the GPT-OSS architecture so special. So the GPT-OSS architecture, if you place it in the context of many other modern models such as Gamma 270 million or Gamma 3, or even for example Quen, um, the architectures of the latest Quen models, it follows some innovations very closely with all of these models. There are not too many extremely novel things they have proposed, especially if you look at the latest models out there. But they use some key things which are currently state of the art. And so it's just good to see that GPT is also, or OpenAI is also using all of these innovations which other players have openly talked about before. So we are predominantly going to be talking about the following things in the GPT OSS architecture. First is with respect to token embeddings. Second is with respect to normalization, which is also called as RMS Norm. Third is multi-query attention and grouped query attention. That is what we are going to see. Then we are going to see sliding attention. That's the fourth thing. Fifth is rotary positional encodings or rope. Then one of the most, I wouldn't say extremely important innovation, but a new thing compared to all the current models is attention bias and attention sinks. And the way GPT OSS actually implemented this. We are going to spend time on this. The seventh thing we are going to learn about is mixture of experts and how they constructed their mixture of experts model. What's the sparsity factor which they used, the activation functions which they used in the feed forward neural networks or their experts. And then we are going to understand the entire architecture workflow of GPT OSS. So there are 9 steps which we have to sequentially go through in the architecture part. This is like diving deeper into the brain of the GPT OSS architecture, right? So if you go to the OpenAI GPT-OSS repository, many things which I'm mentioning right now have been mentioned in code over here, but it just again the same thing, very difficult to understand from the code how things are implemented, what do things even mean, etc. And that's why I believe this deep dive is very important. Let's get started. So the first thing is token embeddings, right? So now what we are essentially doing is that we have tokenized the text. And imagine you have one input sequence like this. I We have one input sequence which goes through the model and we want to do a prediction. That's what we are learning about right now. What exactly happens through this input sequence as it goes through the model, and how are we going to get the predictions which we will ultimately compare with the ground truth. That's exactly what we are trying to understand right now. So we have already looked at the first thing, which is the tokenized text. The input sequence is converted into a bunch of token IDs. We already have that. But there was one innovation which actually happened in 2014, and that's word to vec. So what people realize through this innovation is that words can be converted or can be represented as vectors. But the really cool thing about this is that words which have similar meaning will have vectors which are closer to each other. That's a beautiful thing to know. So basically, you can encode some information about the meaning of words into these vectors, so that finally when you visualize these vectors, you'll see that words which mean the same thing lie closer together in vector space. um, and we have actually written a blog about this on our Substack, which is an amazing blog on word embeddings and how we got to that point. So here's the whole idea, right? These are words which are represented together in vector space, and initially every word will be a random vector. We don't know what's the ideal representation for each word. In word to vec, they actually trained. Let me show you word to vec again. In word to vec, what they actually did is they started out with random vectors for each word and then trained neural networks uh, to make sure that vector representations of words and its neighbors should be closer to each other. That's how they trained the neural network, and then the parameters of these vectors changed. That's how word to vec did it. The way we are going to do it in language modeling, or the GPT-OSS is a replication right now, is we are going to start off by assuming every token ID has a random vector associated with it, and we are going to train the vector parameters as trainable parameters with the rest of the model itself. We are not going to use a pre-trained word to vec encoder at the start. So when you see this token embedding layer, it essentially just means you take your token IDs and convert it into a high dimensional vector space. And then later we hope that those parameters are optimized, and then words which carry similar meaning will lie closer to each other. So when you have to design an embedding layer like this, you have to decide the embedding dimension, right? So if you take a look at GPT OSS architecture, they used an embedding dimension of 2880. So I'll just mention it over here. They essentially took the token IDs and converted it into a 2880 dimensional vector space. So for example, we have already started looking at our stories, right? So let's see. This was our one story, and let's say I took a look at the token ID for day, which is 2163. This 2163 will be converted into so this 2163 will be converted into a vector which has 2880 dimensions, which are random currently. So I mentioned them as tunable parameters here. And these parameters will be tuned as the training proceeds, so that this vector, which this token which I've seen is for day, right? Day. So essentially day, then night, which carry similar meaning, morning, they will have vectors closer to each other after everything is trained. This is 2163. So yeah, 216 and 3. So that's the whole idea of this first step, which takes words and converts it into high dimensional vectors so that they can encode meaning. Okay, this is nothing new, and it's used in all transformer architectures which have been released from 2018, 2019, 2020 onwards. It's just that previous architecture had a positional embedding layer also after this. So what previous architectures did is that along with token embeddings, they also had a 2880 dimensional positional embedding, and they added token embedding plus the positional embedding, which gave an input embedding. The input embedding is the one which is then passed to the model, but positional embeddings dilute the semantic information carried by token embeddings this way. So then later people figured out that instead of adding positional embedding here, we will add the positional embeddings in the attention mechanism or in the attention layer, and we'll add them such that they don't change the magnitude of anything, they just rotate the vectors. That's why these are called rotary positional encodings. We'll come to that later. But I hope all of you have now understood this first step out of the 9 steps which we are going to look at, and that's token embeddings. That's done. Now let's move forward. The second thing which we have to understand over here is RMS normalization. And this is different than the normalization which was previously done. So let's say if you have a vector such as 188.5, whatever. And if I want to normalize this vector, previously what was done is that you just take the mean, mean of this, and you take the variance of this. And then every single value, let me call it xi, you subtract the mean and you divide by the square root of variance. That's the normal way usually to compute or to do normalization, right? But in RMS normalization, things are actually a bit different. What is done is that you first, let's say this is a vector. Let me reduce the size of this pen a bit. Let's say this is a vector. You first take the uh, magnitude, like you take 2 square plus minus 6 square, divided by 2, and then you take a square root of it. So this is called a root mean square. So mean square, essentially first you do mean square. What does this mean is that you take a mean of the squares, 2 square plus minus 6 square, and then you take a square root of it. So this step is where the RMS norm comes in. You first find the RMS of this vector, and then you divide the vector with the RMS value. That's the basic version of RMS norm. So essentially, if you have a vector like this one, the same thing, 188 point minus zero point 0.5, or what did we have here? We had zero point 0.5, right? 188.5, etc. What you do is that first you square all of this, or let's say there are 100 elements here. First you take the mean of the square of all of this. That's the mean square part. And then you take a root. So that's my RMS value. And then what I'm going to do is that I'm going to make sure every xi is divided by this RMS value. Right? That's the most simplest version of how RMS normalization is actually implemented. But now what we do when we deal with language models is that after we divide with this RMS value, there is also a scale parameter which is introduced. And in some cases, we also have a shift parameter which is introduced. So when we have a scale parameter which is introduced, what it means is that you simply, let's say the scale parameter is 1. Then you add the scale parameter element wise to, actually, let's, the scale parameter should have the same size as the vector size. So if the scale parameter is zero point 0.5 and minus zero point 0.2, you first add 1 to this. So it will be 1.5 and zero point 0.8. And then you multiply the vector element wise with the scale value. And then you can also add a shift parameter which you add to this. So then it's also added element wise. And then you get the final answer. So you can think of these as just free parameters essentially, or trainable parameters. When you do the normal RMS normalization, so this dot means element wise multiplication with 1 plus scale, and then you can also add a shift parameter. The reason this scale and shift is done is just if normal normalization does not match the underlying distribution of the language data, maybe adding a simple scale and shift will actually make the prediction a bit better. So these are just trainable parameters which we have added. Now, why is this normalization being preferred a lot more currently compared to the previous version of normalization, which I just told you? I think the reason is because it is slightly computationally faster, and the performance also has shown to be a bit better with RMS normalization compared to the previous version of normalization which was used. But I've seen that in all modern architectures, including Gemma 3270 million, if you take a look at their architecture, right, they are also using RMS normalization. So I see this trend going forward more and more, that latest language models are relying on RMS normalization than the standard way of doing normalization. So that's the second thing. And wherever you see RMS normalization, it's just that vector which is normalized. So whenever we have a normalization here and also in the output block, you should note that it does not change the size of the vector. The dimension of the vector remains the same. It's an in-place operation. There is no interaction between different vectors also. We are just looking at one vector and we are updating it. Why is normalization done in the first place? It just makes the gradient training a bit more smoother. Otherwise, there are issues such as internal covariate shift, etc. We don't need to get into those right now, but just remember that normalization blocks are extremely important in language model training. They look to be simple, but you'll see that they show up in several places in modern architectures. There have been some recent papers which argue to get rid of these blocks in terms of by replacing them with dynamic tannage. So it's called, I think it was from Jan LeCun's group, dynamic tannage, which is transformers without normalization. When I release the code to all of you, the nano GPT code, you can feel free to just replace the normalization layers with the dynamic tannage which they have introduced. So with this, we have finished two steps, the token embeddings and the RMS normalization. Now let's come to the third step, which is equally important, and that is multi-query attention or grouped query attention. So GPT-OSS actually used grouped query attention, and they used a ratio of 8 is to 1. I'll actually explain what that means. Um, but for you to actually understand this, you'll first need to understand multi-head attention. Then I'll quickly explain to you about this thing called as the KV cache, and then we will essentially talk about, okay, why do we need to think about multi-query and group query attention. But first I want to check whether they did use a ratio of 8 is to 1 or not, because I don't want to have a wrong mention here. GPT OSS grouped query attention ratio. Yeah, so it's 8, right? Okay, I so which is correct. That's essentially 8 is to 1. You'll soon understand what this ratio actually means. But first, as I mentioned, we need to start understanding what is multi-head attention. Now, as I mentioned at the start of this lecture, I am not going to go into the attention mechanism in a lot of detail. I'm going to explain to you a broad overview of multi-head attention, KV cache, and then why we need group query attention so that you appreciate what GPT OSS has done. So later, whenever you see GQA, you understand what it means. So the idea of multi-head attention starts from this fact that we really need to capture the context, right? Um, we need to capture the context and we also need to capture it from multiple perspectives. That's why there are multiple heads. So first, let me talk about how this mechanism operates. So let's say if you have the some input like the artist painted the portrait of a woman with a brush. Before it enters this attention block, before it enters this attention block, uh, every word is now an embedding, right? Based on the embedding dimension. GPT OSS use 2880. So this would be 2880. Now, what happens in the attention mechanism is that we take this input. So the input matrix is now 11, comma 8. We will multiply it with these trainable matrices, which are called as the trainable query matrix, trainable key matrix, and the trainable value matrix, right? Uh, when we multiply the input matrix with this WQ, WK, and WV, we get matrices which are called as the query, the key, and the value. So this is 11, comma 8. When we multiply it with 8 by 4, we'll get 11 by 4, 11 by 4, 11 by 4. Three dimensions here are already fixed. The fourth one can be varied. So for example, this 11 is fixed by the context window, how many tokens can come at one time. This 8 is fixed by the embedding dimension of the model. In our case, it's 2880. So when you do want to do a matrix multiplication, it also fixes the number of rows of these matrices. But the number of columns are a bit variable. Usually models keep the number of columns dimension as the same. So you can assume this to be equal to 2880 in the case of GPT-OSS, but we have an option over here. So we have these queries, keys, and the values. And you might be thinking, why are we doing all of this? And the reason boils down to this fact. Until now, when all of these individual tokens, let's look at these tokens itself. Let's When all of these individual tokens enter my uh, architecture, we have looked at these steps so far, right? In all of these steps, there are calculations which are happening at an individual level, which means there is no interaction between the different tokens at all. That's exactly what the attention mechanism plans to solve. How will the model know how to predict the next token if there is no relation between the words? I need to know that when I look at let's say portrait, right? I need to know that portrait may be associated with a woman, right? So more attention needs to be paid between portrait and woman. When I look at artist, maybe artist painted the portrait. So artist and portrait, artist portrait and painted. This should also have high attention scores. But maybe portrait and the should not have that high attention scores, right? So when I look at tokens, when I look at individual words, I need to know how much attention should I pay to the other words. That's exactly why the attention mechanism is introduced in the first place. So if you look at any particular word, let's say portrait, let me call it the query. That's where these names comes from, query vector. So when I look at one particular query vector, I want to look at all the other key vectors. So when I look at a query, all the other vectors, including these ones, become the keys. I want to look at the other key vectors and I want to find how much more attention or how much attention should I give to the keys. And that is quantified by this formula. When you have queries and keys, you can just multiply the queries with the keys transpose, and then you get the attention scores. So, uh, before going to that, let me also explain the concept of heads. So, here I am showing a single head, right? But in multi head attention, usually these vectors are split into multiple heads. So, each head learns a different perspective. So, here I am using the two heads. So, we are splitting these into two. So, now instead of having one query, one key and value vectors, each head will have its own query, key, and value vectors, right? So now if I look at head number one right now, and I'm looking at portrait, I'm looking at the query associated with portrait. I want to find the attention score between this query and all the other keys. How do I do that? So I first do a dot product of queries with the keys transpose, and that gives me an 11 by 11 matrix, which looks like this. Now this matrix has a particular meaning and it's very interesting. If you look at this 11 by 11 matrix, this is the attention scores matrix. So every element here gives me an attention score. This element gives me an attention score between the and the. This element gives me an attention score between the and off. If I want to look at the portrait and if I want to look at the attention scores between portrait and all the other keys, I just look at this row. So this is exactly what I wanted. I have now got a matrix which gives me, when I look at one token, how much attention needs to be given to all the other tokens surrounding it. So this matrix is called as the attention scores matrix, and we'll get such a matrix for both the heads. What head 1 discovers in its attention scores might be different than what head 2 discovers. Why do we need this? Because we need, what if one attention score is not able to capture the perspectives in a sentence? Let me explain this with an example. Let's say we have this artist painted the portrait of a woman with a brush. Now, this example can be looked at through two different ways, right? Either it can be the artist painted the portrait of a woman using a brush, or the artist painted the portrait of a woman who had a brush in her hand. That's two different things, right? So in one attention scores matrix, let's say this is the head one attention score matrix, it's 11 by 11. Here, if you look at portrait is associated with woman, but not with brush, because it's capturing this perspective. Whereas if you look at this attention score, the attention score between portrait and woman is high, and portrait and brush is also high. Uh, and if you look at brush here, it has an attention score with artist and with. That's fine, which means the artist is using the brush. But this brush has also an association with portrait and woman, which means that the brush is present in the portrait itself. So what I'm trying to illustrate here is that both these attention score matrices are 11 comma 11 matrices. But this is captured by head number 1 and this is captured by head number 2. That's why multiple heads are introduced so that they can capture different perspectives. So you have the head 1 attention scores and you have the head 2 attention scores. After you get the attention scores, then you calculate the attention weights. The way to do that is that you want to make sure that every row has to sum up to 1, because I want to make some quantitative statements like when I look at portrait, give 10% attention to the, give 20% attention to painted, etc. So I want all of these attention scores to sum up to 1. But another thing to note is that if I look at portrait, right, I actually don't know what is going to come after portrait, because we are training the model to predict the next token, right? So when I look at portrait, I can only look at tokens before it. I cannot look at one query token and find the attention scores for tokens which keys which come after it. That does not make sense, right? That would be cheating. A token should not look into the future. So that's why if you look at the attention weights, you will see that above this diagonal, all of these values are set to 0, because we are not looking at those at all. If you look at every token, every query, it can only look at the tokens which come before or at its position. So if you look at now, if this is the one for portrait, right, all these words come before or at portrait, all these words come after, so we do not look into it. So this part which I have marked in blue color right now, that's the future. And I cannot peek into the future. That would be cheating. So this is called as causal attention. Or it's also called as masking. We create a mask which blocks out everything. So for a token, which blocks out everything which comes into the future for a token. For the first token, so let me rub this a bit uh, and use a different color. For the first token, everything which comes after it is a future. So all of this is blocked out. But for tokens over here, very few tokens come after them. So small number of tokens are blocked out. This is called as causal attention. So to go from attention scores to attention weights, we do softmax, we do causal attention, and two more things are done. Scaling is done, so we divide by square root of the keys dimension, and a dropout layer is also applied. Dropout is randomly switching off certain weights to improve the generalization performance. When we want to use the model on queries which have or prompts which have not been seen before. So that's how we get the attention weights. Then there is one final step. The attention weights are multiplied with the value vectors which I have computed for different heads. And then we get something which is called as the context matrix. We get a context matrix for head 1 and we get a context matrix for head 2. So you can think of the context matrix as the final matrix which captures all the perspective of from head 1, and this matrix as all capturing all the perspective from head 2, and then we merge the context matrix for both the heads, and this is our final context matrix. This is the final result which comes out of the attention block. So when we come out of the attention block, the vector which goes in is called as input vector. When it comes out, it's called as the context vector, because now the input is a lot more enriched with context, right? And this context vector is also very interesting to note, because if you look at portrait, right, it now contains the perspective from head 1 and perspective from head 2 both. So now both perspectives are maintained in one vector, so it's a lot more richer vector. And this vector also contains information of other tokens. Now it's the only place in the LLM architecture where there is cross interaction between neighbors. That's why the context is captured a lot better, and that's why the attention mechanism was a game changer for language modeling. So what I just explained to you was multi-head attention, right? We have different heads, each head captures a different perspective, and we have input vectors which are converted into context vectors when they come out of the attention block. I hope all of you have followed this so far. So then what is multi-query attention and what is grouped query attention? It turns out that uh, when you want to predict a new token, you have to calculate the keys. You have to calculate the keys matrices and the value matrices every single time when you want to predict a new token, and that leads to a lot of repeated calculations. So people figured out something which is called as the key value cache. So what key value cache essentially means is that instead of calculating the keys and the values every single time, you maintain a cache and you store the keys and the values you have computed for the previous tokens which were inferred. So whenever a new token is inferred, you just take the uh, previous keys and the value which has been stored. So the number of computations during inference reduce, right? The issue with having the key value cache is that the more the dimensions you have in the keys matrix, the value matrix, you increase the memory of whatever is stored. And the memory is usually, or one factor which plays into the memory is, there are four heads, right? And each head has two dimensions. And all of these values are different from each other. So naturally, every value needs to be stored separately. And if every value is a 32-bit or a 16-bit floating point, it takes that much memory. It contributes to bytes that much. So then people figured out that, okay, what if I want to reduce the memory requirement of the key value cache? Because that suddenly became a problem. Key value cache started taking more memory, then the inference compute efficiency started to decrease. Then everyone started thinking that, okay, how do I reduce the memory footprint? One key parameter which comes up in the memory footprint is the head number multiplied by the dimensions, right? Uh, so all of these heads have different values over here. So people then thought that what if I impose a structure that head 1, whatever values are there in head 1, that's the same as head 2, that's the same as head 3, that's the same as head 4 for the keys as well as for the values. So this is what people proposed. What if head 1 key weight matrix, and naturally the key matrix also, head 1, head 2, head 3 and head 4 have the same content. Values matrix head 1, head 2, head 3 and head 4 have the same content. So essentially what if they share their parameters? Now that would naturally drastically reduce the memory requirement by 4 times, right? Because we don't have to save the parameters separately for each head. We just have to store it for one head and use the same across the heads. So naturally that would bring down the memory footprint by an order of magnitude. But what's the trade-off? Of course, the trade-off is, why are different heads introduced in the first place? To capture multiple perspectives, right? The moment you share parameters, that ability will be reduced. The model will not be able to analyze the text with a nuanced perspective. And it might only look at the text with one perspective, so the performance of the model might be hampered. So this idea of sharing the parameters across heads is called as multi-query attention. So remember, the sharing of parameters across head is only valid for keys and values. For the queries, the parameters are separate across different heads. So that's fine, because the query matrix does not contribute to the key value cache problem. That's why it's called multi-query attention, because the parameters are shared across all the heads. That's called as MQA. So as we have seen about MQA, it actually reduces the KV cache memory footprint, but it also hampers model performance. So then people started thinking that, okay, I don't want to hamper the model performance, right? Uh, but I still want to reduce memory. Can I think of a trade off? And that is where the idea of GQA was born, which is called as grouped query attention. So the idea was, let me think along the same lines, but now instead of all the heads sharing parameters, what if I divide the heads into groups? So what if this became group number 1 and what if this became group number 2? So instead of all the heads sharing parameters, group 1 and group 2. So group 1 will share parameters, group 2 will have different parameters completely. Uh, so that's like kind of in the middle ground, right, between multi-head attention, in which all the heads have different parameters, and multi-query, where all the heads have same parameters. So here, every group, so group 1 will have the same values, group 2 will have different values. This is called as grouped query attention, GQA. So remember, we interacted with ChatGPT and we asked that uh, GPT-OSS group query attention ratio. And here you will see that ChatGPT mentioned 8. Each key value head serves 8 query heads, the group size of 8. So what this actually means is that if you take a look at number of heads which GPT OSS actually had, the number of heads which they have is 64 attention heads, right? Now what it means to have a grouped query attention of ratio 8 is to 1 is that there will be 64 heads. There will be 64 heads, and each head will have some dimension. So let's say this is head number 1, this is head number 2, this is head number 8, um, and let's say I'm printing out the WK here. This is WK for head 1, for head 2, for head 8, and similarly there will be 64. So what it means is that this whole thing is now group 1. 8 heads are in one group. The remaining 8 heads are in group 2. Similarly, there will be 8 such groups, and each group will share parameters completely for the WK and for WV as well. That's what it means to have a ratio of 8 is to 1. So the way it's mentioned in practice is that 64 query heads. So as I mentioned to you, nothing changes for the query, because even here the queries had 4 heads, that is fine. Head 1, head 2, head 3 and head 4. But now the keys and the values effectively have only 2 heads, because we have formed 2 groups over here. So this is a 2 is to 1 ratio, but GPT OSS used an 8 is to 1 ratio. Yeah, it's mentioned over here 64 query heads are paired with only 8 key value heads. So each key value head serves 8 query heads, and that is why it's a group size of 8. Okay, so I hope all of you have understood grouped query attention, right? There is still a trade-off. So the memory footprint of group. So let me draw a bar graph about the memory footprint now. If you plot the memory footprint of the KV cache, now all of you should be able to answer this, right? Which is the one out of MHA, MQA, and GQA to have the highest memory footprint? You can pause the video here if you want to think about it. But MHA actually has the highest memory footprint, followed by GQA, followed by MQA. And what about the performance? So performance is capturing perspective, then capturing the different diversity in the input, etc. Again, here the MHA will have the maximum performance, followed by GQA, followed by MQA. So MQA actually does very well with the memory footprint because it has a very low memory footprint, but it's quite bad with performance. MHA does quite bad with memory footprint, but it's great with performance. And grouped query attention is the best of both worlds. It lies in the middle. And that's why many modern architectures go ahead with group query attention. Even I think Gamma 270 million. It's a very small language model, so they went with multi-query attention because they really wanted to reduce the KV cache memory footprint. And they also wanted to reduce the number of trainable parameters actually. Multi-query attention, group query attention also reduces the number of parameters you can train, because you just share the parameters across different heads, right? So this is the third part which I wanted to explain to you, which is essentially grouped query attention. And I hope all of you have understood and followed this part thoroughly. This is one main concept in uh, the GPT-OSS architecture. We still have six more parts remaining, which is sliding attention, rotary positional encodings, then attention bias and sinks, and then finally we'll move to mixture of experts, the output layer, and GPT-OSS entire workflow. Many modern language models have actually been using a variant of the causal attention mechanism, and that essentially is called as sliding attention. So let me actually explain to all of you what sliding attention exactly means. In the previous lecture, if you remember, we looked at the causal attention mask, right? And let me mark that mask for all of you. Essentially, all the elements which have been marked as 1 over here, those are the elements which are masked out, which means that every token cannot peek into the future. Tokens can essentially only look at their position and the tokens which come before them, right? So this is called as the full causal attention mask. But now if you take a look at computations itself, imagine that the context window is n here, and the number of computations which will be made, that will be n square divided by 2. So although this half is masked out and you don't need this, that does not reduce the order of magnitude. It just divides it by 2. So the number of computations which will need to be made will be n square divided by 2. And if you think about the context window which they use is actually it's a huge context window. It's around 131,000. So even if you take a random context window which is slightly smaller than this, it will be about 14,000, 15,000, or even 131,000. It will be n square, right? That's a lot of computations which need to be made. So then can we essentially bring down this order from n square to n multiplied by w? So can we make this linear in n instead of scaling quadratic in n? And this w will be a window parameter. I'll mention to all of you um, what that actually means. Uh, so let me actually first replace this 14937 what did we have earlier, 14976 with 131k, which was the actual context. So instead of doing a causal attention mask like this, people thought about a variation to this where they asked that, okay, we restrict every token from looking into the future. We will maintain that. But at the same time, what if we restrict every token from looking too far back into the past as well? Um, so take a look at this token, for example. This token, for example, if we did normal variation of causal attention, it cannot peek into the future. So it only has to look at all. So it cannot look at this token. That's fine. But now what if we restrict this token from looking too far back into the past? So what if we restrict the token from looking at these three tokens? So in a way, each token cannot peek into the future and it cannot look too far back into the past. It can only look at a small window. That's why it's called sliding window attention. Why the sliding part will come, I'll let you know. So the sixth token will only look at this window of 4 tokens. Now for the fifth token, of course, the fifth token cannot peek into the future. So we'll mask out these tokens which it cannot see, and it cannot peek too far back into the past as well. So it only looks at this window of four tokens again. The reason it's called sliding is that this window now, it just slides or shifts to the left hand side as we move up the tokens, but its length remains the same. It always remains equal to 4 as we shift up, right? So this is called as sliding attention. It is causal attention, but it makes sure that we do not peek far back into the past. And if you now take a look at this matrix, we only have to now compute, we only have to do computations for this trapezium shape over here. That's it, this shape. And if you take a look at the order of magnitude of the computations, that's now, of course, n, which is the diagonal, but this width, which is w, which means what's the sliding window uh, magnitude which we want. Here it's 4 tokens, right? That's called as w. GPT-OSS used a sliding window of 128, which means that although the context layer is 131,000 tokens, every token can only look at 128 tokens before it. Now let's see how much computations does it reduce for us, right? So if I go to a calculator right now, and earlier this was 131 multiplied by 1, actually 131,000 multiplied by 131,000, those many number of computations, right? So now what if instead of 131,000 multiplied by 131,000, it will be 131,000 multiplied by w, which is 128. So now what if I do a ratio? So I'll copy this and I'll divide 131 multiplied by 131,000 multiplied by 131,000 divided by, okay, let me do it another window. So this is 131,000 multiplied by 128, right? So that is 16. So I'll divide the original with this divided by 16768, and I have three zeros. You see, so that's a reduction already of around 1,000 times the number of calculations which need to be made. So that's why sliding window was introduced, to reduce the number of computations which I need to do. But of course, it brings in a trade-off, right? And the trade-off is that what if the context, what if to retain all the context, the tokens have to look way far back into the past. But the more the training data we have, maybe such very long contextual relationships won't be that much. And even if we miss it out in one area of the training data, we might recapture it when we go to another place in the training data. Uh, However, whatever I explained to you right now, that's the key essence of sliding attention. So when you go to the GPT architecture right now, this attention, now you might be asking, are all the transformer blocks, do all the blocks have the sliding attention? Now pay very close attention here. This processor block which I have shown here is a transformer block. And as I mentioned at the start, GPT-OSS 20 billion has 24 transformer blocks, and GPT-OSS 120 billion has 36 transformer blocks. So essentially now, there will be, if we look at the 20 billion, there will be 24 transformer blocks like these. So we need to decide which of these transformer blocks have sliding window and which of them have the full causal attention. What Gamma did is they had 18 transformer blocks. So they used 15 sliding and only 3 full layers, Gamma 270 million. What GPT-OSS did is that they used alternate sliding and full layers. So for example, if the first transformer block had a full layer, the second will be sliding. Third will be full, fourth will be sliding, fifth will be full, sixth will be sliding. So it was alternate like that. So if you were to, okay, do back, uh let's go back to the section where we left off. Yeah, so what I was mentioning was, if you had, let's say this is one transformer block, this is my second, this is my third, etc. And we had many such blocks, let's say, right? So the way they did it was the first block had the full attention, the second block had the sliding variation, the third block again had the full variation, the fourth block had the sliding. So they had an alternate variation, which means for the 20 billion we had 12 full causal attention blocks and 12 sliding attention blocks. And for the 120 billion we had 18 full attention blocks and 18 causal attention blocks. All right, so that was the fourth building block which we discussed in the GPT-OSS architecture. Now let's come to the fifth building block, which is rotary positional encodings. As I mentioned before, earlier we used to have absolute positional encodings which were added to the token embedding layer over here. Absolute positional encodings were added to the token embedding layer, but there are two issues with this. First, it changed the magnitude of the token embeddings, and second, it contaminated the semantic information learned by token embeddings. So people decided that, okay, let go of this. I will use position embedding where it really matters, which is the attention mechanism. So the way rotary positional encoding works is that when we calculate the attention scores, those are between queries and keys, right? So position definitely matters. So what we will definitely do here is that we'll look at the query vectors and we'll look at the key vectors, and we will rotate these vectors to inject the information regarding the position. We don't change anything related to the value vector at all, because that does not come up to calculate the attention scores. Remember, to calculate my attention scores, I only need the uh, query vector and the key vector. So if I want to encode information related to position, I will do it in the query and the key vector, because that will ultimately then come into my attention scores, which is what I want ideally. I want the information of position to be included somewhere. Why do I want this? Because, well, take a look at this sentence, right? The dog chased, let's say I take this sentence, the dog chased another dog. It could not catch it. Now, if I look at this it, which I am right now marking in this green color, and if I look at the second it, which I'm marking in red color, this first it refers to the dog, refers to the first dog, and the second it refers to the second dog. So clearly they are referring to different things. But if I just do token embeddings, both of this will have the same meaning. So they have the same vector. So ultimately, when my context vector is formulated, I want the context vector for this it and this it to be different from each other. Ultimately, when I get a context vector for it and it, I want it to be different. I don't want it to be the same. So the way I inject that difference is in the queries and keys through the position. So the first it and the second it comes at different position. So as I'll show you, their query and the key vectors change. So their attention scores change, and so their context vectors will eventually change. That's the whole idea. So how do we inject positional information into the query and key vector? It happens as follows. So let's say we look at the dog chased another dog. Now this dog and this dog are also different. They come at different positions. So we want to inject this positional information. So the way it's done is that let's assume that these are query vectors for the dog chased another dog. And I want to inject different positional information in all of these so that we have some knowledge that these tokens come at different position. So first I look at the first query vector, and it has 4 dimensions for now. Ideally, when we look at OSS, GPT OSS, this would have the number of dimensions which is equal to our embedding dimension, that's 2880. But for the sake of simplicity, here I am looking at a 4 dimensional vector. We divide it into groups of 2. So x1, x2 will be one group, and x3, x4 will be the second group. And then what we are going to do is that we are going to, let's say, represent this in a vector space. So this is x1 comma x2, right? To inject the information of position, we are going to rotate this vector by a magnitude theta, and we'll rotate by an amount which depends on position. So the formula with which we'll rotate is given by this. This theta is wi into p, where wi is 1 divided by 10,000 raised to 2I divided by d. So this multiplied by p is the amount with which I'll rotate. Uh, okay, so now you might be thinking that where exactly is the position injected here, right? So two uh, there are two variables here. There is the index I and the position p. Those are the two things which you need to keep in mind. So position p is of course the position at which that query appears. So this is position number 1, this position number 2, 3, 4, 5. So for this dog and this dog, the rotation amount will definitely be different because this p differs. This first dog comes at position number 2, so this comes at p equal to 2. Or let me write a text here. So this dog comes at p equal to 2, and this dog, it comes at p equal to 5. So that's why the angle with which these two vectors will be rotated will be different for sure. But you might be thinking, what is I? So I is essentially the index for one position. So if you look at the position is fixed, but x1, x2 appear at index number 1 and x3, x4 appear at index number 2. So even for one position, x1, x2 will be rotated by a different amount than x3 and x4. This I comes in the denominator, right? So essentially, the more deeper you are along the dimension, the less you will be rotated by. The earlier indices will be rotated by a larger amount. Similarly, the deeper you are in terms of position, the more you will be rotated by, because theta directly depends on position value. So x1, x2 is rotated by theta, x3 and x4 is also rotated. And remember, the amount of rotation of x1, x2, x3, x4 is not the same because their index actually differs. And this d is my total dimension, which is 20. I keep forgetting this, but it is 2880. That's the total dimension. So this d, which I just showed to all of you in the denominator, that actually remains fixed. So x1, x2 is rotated to form this new vector, which is x1 dash and x2 dash. This vector here. x3, x4 is rotated. X3, x4 is rotated to form this new vector, which is x3 dash, x4 dash. So essentially, x1, x2, x3, x4, they are now transformed into another vector, which is x1 dash, x2 dash, x3 dash, x4 dash. The beauty of this vector is that its magnitude is not changed because we are just rotating vectors. Magnitude does not change, but still the direction changes. So the effect of position is now being encoded that way. This is what we do for all the query vectors, and this is what we do for all the key vectors to include positional information. So to include positional information, we don't add any vector to the query vector. We effectively just rotate parts of the original query vector, and hence we maintain its magnitude, thus avoiding the vector polluting issue. In sinusoidal embeddings, as I mentioned, position embeddings are added to the token embeddings directly, which pollutes the vector. So this avoids that, because we are not adding anything to the token embeddings. First of all, we are integrating this rope step in the attention mechanism, and secondly, we are rotating. We are not changing the magnitude of the underlying vector. Now, some key things to note based on this formula is that this formula, the rotation formula, depends on the position, depends directly on the position and inversely to the index, right? So here is just a simple schematic. Essentially, if you, so here the dog chased another dog, right? So as you go from left to right, the position increases. So what I'm trying to illustrate here is that the higher the position, the larger is the rotation, because it directly depends on p. This means that closer queries have similar positional embeddings. as they should. And further queries have different positional encodings. This is a good intuitive knowledge to encode. Second thing to mention is that the lower index values change fast with position, while the higher index values change slow. So if you look at one position right now, if you have a lower index, since I comes in the denominator, their rotations will be higher. But if you go down here, if you have a higher index, you will see that the rotations will be slightly smaller. Uh, yeah, so lower index changes fast. So one thing to note here is that if you focus on position number, lower index changes fast with position. Yeah, if you look at lower index, if you look at index number one, and if you see how it changes with position, it changes fast with position, right? Quickly, you can see the circle size is increasing here for lower indices. But for higher indices, you can see that most of the circle sizes kind of remain the same. So the key thing to note is that lower index positional values change fast with position. So they are called high frequency oscillations, and higher index positional values change slow with position. So they are called low frequency oscillations. Why do we need two different level of oscillations? Well, lower index quick oscillations ensure the model captures small shifts. For example, take a look at this sentence. I just told her the truth versus I told her just the truth. These are quick oscillations which need to be captured. So the lower index fast oscillations capture this change brought about by varying the position of the word told. Whereas if you have certain sentences uh, where you want to preserve relationships across different positions and not unnecessarily change the positional information embedded or unnecessarily inject too much positional information. For example, if you take a look at this, Einstein developed the theory of relativity. This breakthrough reshaped physics. Now, breakthrough refers to the theory of relativity, which comes many words earlier. So, higher index low oscillations capture long range context dependencies because they don't oscillate very quick. So, some key points to note is that lower index frequencies ensure model captures small shifts, and higher index components ensure that even with large position differences, relationship is preserved. So that's why these smaller shifts are captured and larger shifts are also captured. That's why rotary positional encodings also makes a lot of intuitive sense. And almost all the modern language models have included rotary positional encodings as a key part of their architecture now. Now we come to the sixth uh, major element of the GPT-OSS architecture, and that has to do with attention bias and attention sinks. So let's start learning about this now. Now we come to attention bias and attention sinks. This was not implemented in Gemma 3 270 million, and as of my knowledge, it's not implemented in latest Quen models also. It's a new thing which has been implemented in GPT OSS, and it would be good to know about these two terminologies. So, to actually explain attention bias, we need to initially start understanding attention sinks because that is the terminology which came first, and after this was attention bias, which actually was used by GPT OSS. So, if you look at attention sinks, right? This was the first paper which mentioned about attention sinks. So let me start by talking about why they claim that we need attention sinks in the first place. So essentially, what the authors found out was, let's say this is a pre-trained Llama 2 7 billion model, and this shows the attention logits for 16 sentences compared to the 16 sentences, right? So over 256 sentences, each with a length of 16. Uh, so that's why it's a 16 comma 16 attention scores, right? So if you look at, so they have shown layer number one, which is the first transformer, layer zero, first transformer block, second transformer block, third transformer block, and here we have 9th, 16th, 23 and 31. So transformer blocks which are a lot more deeper. So one key thing to note here is that in the initial layers, uh, recent tokens receive more attention, right? Because they are more darker. And that's probably fine. When you look at a sentence, more recent sentences to that sentence will receive more attention. But, and you can see some attention has been given to other tokens as well. But if you take a look at deeper layers, there is one very interesting phenomena which happens over here. Take a look at this red line over here. In all of layer 9, layer 16, layer 23 and layer 31, there is one red line or red vertical line at the start, which means that the model essentially heavily attends to the initial token. This means that all the subsequent tokens, no matter what the token is, they pay a lot of attention to the initial tokens, because this vertical line actually corresponds to the first token. This vertical line corresponds to the first token. So all the subsequent tokens pay a lot of attention to the first token. This phenomenon does not happen in early layers, but it happens a lot in future layers. Now here is where the problem arises. If you are using sliding attention, which I mentioned to you, and let's say if you are someone like token number 6 over here, okay, in deeper layers, you want to pay attention to the first token, which I just showed you right now, but you cannot do that because you don't have access to it. So what do? Then you dump all of your information into these intermediate tokens which are available to you. That does not really make too much sense. You are essentially dumping noise into tokens because you wanted to just, first of all, put all that attention to the first token. But token 1 is inaccessible to you. So you dump all that attention to whatever is accessible to you. So the attention scores of all these tokens will unnaturally increase, and that will confuse the model, that will lead to noisy training updates. That happens with this token as well. As you go into deeper transformer blocks, deeper layers, this token also wants to give attention to the earlier token, but for the first token, but it cannot do that because this is restricted for it. So it then gives attention to the middle tokens. So the attention scores for these middle tokens actually increase a lot, which leads to noisy updates. And that is something which we want to prevent. So the authors introduced the concept which is called as attention sink. So what they mentioned was that what we can do is that decide that I want 4 attention sinks. So we have the sliding window. That's fine. Let's keep that. We have the sliding window. Where was that? Yeah, we have the sliding window. That's fine. Let's keep it. But let me add a column at the start here. Let me add a column at the start where that attention can be diverted to. And the way they did this initially is that they added these tokens itself. So in the generated tokens, what could be done is that there could be certain number of tokens which could be designated as attention sinks. And when we create the sliding window uh, attention mechanism, these tokens are fine. It's fine to attend to these tokens. So then the attention won't be randomly distributed to the intermediate tokens. Instead, these attention sinks will get all of that extra unnecessary attention, and then you can then forget about it, and then only you can consider these tokens and their attention scores. That's how it works. The reason it's called as a sink it because it's absorbed all the heat, or it absorbs all the noise, it absorbs all the attention noise. These attention sinks absorb all of the extra unnecessary attention which tokens in deeper layers want to provide, so that when you later actually calculate the attention scores, you still only look at these tokens, but their values now won't be unnecessarily inflated because my attention sinks have captured all that attention. And why do you keep these attention sinks at the start? The reason we keep it at the start is because of these diagrams. What people figured out is that as we go deeper and deeper into the LLM architecture, the initial tokens seem to get a lot of unnecessary attention, which does not really make too much sense. So we should not use it into the attention mechanism calculation. That's the idea of an attention sink. So if you uh, actually look at heat sink animation, uh, a heat sink animation essentially I wanted to show because that's the place where the heat sink absorbs all the heat. It's similar to noise being absorbed. So if you take a look at this, for example, maybe this is the sink where all the noise heat is absorbed, and so you can think of the attention sink as absorbing all that unnecessary attention noise so that my actual tokens don't suffer, and then I get the correct attention score matrices. uh, all right, so this is called as attention sink. Then you might be thinking, what is attention bias? So attention bias is what GPT-OSS has actually implemented. What it means is that they did not really have tokens. They did not really have tokens which could be attended to. So instead, they directly operated at the level of the attention scores matrices. So instead of having some tokens here and designating them as attention sinks, what they did is, let's say we have these attention score matrices, right? They added one more column to it, which was called as the attention sink. Now, this attention sink will naturally capture a lot of unnecessary attention given to those earlier tokens. That is fine. And so you can think of this as the attention sink here, right? As I mentioned to you, now we add an attention sink over here, which means that now this sixth token which we saw, it can pay attention here, no problem at all. It can pay attention here. Fifth token can also pay attention over here. So we add one more extra column over here. So this column actually absorbs all the unnecessary attention. So we still go ahead with the sliding attention, but now these tokens won't unnecessarily get this additional higher attention scores. That's the whole idea. So if you want to look at it with a simple example, let's say we look at the cat sat, and if this is the attention scores matrix, what we do is that we actually add this sync over here, right? Um, and then we take, so now instead of 3 rows and 3 columns, it essentially becomes 3 rows and 4 columns. So now if you look at, let's say you take a softmax of all of these, and if I want to look at the row of cat, once you take softmax, maybe it becomes this. It all adds up to 1. But this is the score by the attention sink, so we neglect it. And then finally, we only look at these three anyways. So now you see what has happened, this 0.72, which might be unnecessary information that's being absorbed by the sink. And so although these remaining values are a bit small, that's fine. We have not captured unnecessary noise or unnecessary attention noise. And then we operate as normal with these three tokens. So you see, we add something, we let it take all the heat, and then we remove it. So it's like adding someone to your team who deals with all the difficult things, all the negative things, and then you get rid of that. That's what attention sinks are for. Attention sinks, and here it's called attention bias because these values are called as bias values. We don't actually add tokens like it's done in attention sink. We add these bias values. These bias values absorb the unnecessary attention so that the other values attention remains undiluted. And now it's fine even if these attention scores don't sum up to 1. At least they are not affected by unnecessary higher attention values. So the way it's done is that we get the attention scores. We then add a sync column, which is a bias column. This is also trained. And then we apply softmax to tokens plus the sync column. And then what we do is that we drop the sync and it absorbs some probability along with it. That's fine. And then we only keep the remaining tokens. Then we do the context vector calculation, and then we proceed normally as we would have. But when you go to the architecture, you will see that we have specially mentioned here attention sinks. Attention sink essentially means, okay, we are dealing with the sliding window, that's fine. But I am also making sure that my attention sink essentially absorbs all the unnecessary attention which is paid to the earlier tokens. Especially, we saw that this problem happens in deeper layers, right? In deeper layers, a lot of attention is paid to the earlier tokens. And we want my attention sink to essentially absorb all of that attention. So the way to do that is that instead of adding separate tokens as sinks, we can add bias terms to the attention score matrices. We take the softmax with this added bias term, let it absorb some probability which was not needed anyways, and then we get rid of that term. So what remains are these undiluted attention scores. They don't sum up to 1, but that's fine. Why don't they sum up to 1? Because the sink has absorbed some weight or some probability, so the remaining is dampened. I hope all of you understood how attention sinks actually work in GPT-OSS. They are very important to explain because that was something new which was done in GPT-OSS, which was not done when we also covered Gamma 3 or Gamma 3 270 million. And remember that these bias terms are learnable parameters. We don't know their values earlier, but they are learned like the rest of the parameters. Now, only three parts are remaining: mixture of experts, the output layer, and the entire architecture workflow. Three parts are remaining in this GPT-OSS, assembling GPT-OSS architecture. So now let's move forward towards the mixture of experts. The simplest way to think about mixture of experts is essentially we replace the traditional feed forward neural network module, which is present in the transformer architecture. And what do we replace it with? We replace it with multiple feed forward modules. So basically, if you look at any traditional transformer architecture, once you come out of the attention block, then here you have a feed forward neural network. So for example, the feed forward neural network looks something like this. The feed forward neural network has an expansion layer. The feed forward neural network has an expansion layer like this, which I'm calling E, and it has a contraction layer, which I'm calling as C, right? That's usually the way it happens in a traditional transformer architecture. What GPT OSS has implemented, and this is what many modern language models do, is that instead of one feed forward neural network, they have multiple feed forward neural networks. So then you might be thinking, okay, this really complicates things, right? First of all, how do the dimensions match if I have multiple feed forward neural networks? And secondly, are we just increasing number of parameters? So one speciality of this feed forward neural network is that the input dimension and the output dimension is the same. Now, when we have multiple feed forward neural networks, the input and output dimension is still going to remain same. We are simply going to add the outputs from different neural networks. The second question about parameters, increasing number of parameters, to answer that question, the only answer is called sparsity. So essentially, we'll have some sort of a routing mechanism. And what the routing mechanism will do is that based on the question which has been answered, instead of activating all the experts at once, it will only activate a select group of experts for every token. So that is the concept of sparsity. Most of the experts will remain dormant or inactive. Now, if you look at GPT OSS and the way they have implemented their mixture of experts architecture, they have 128 experts in the 120 billion architecture, and they have 32 experts in the 20 billion architecture. And in both of these, there are four experts active every token, which means that even if it's a 20 billion architecture, uh, only 3.6 billion parameters are active during inference, which means that whenever a new token comes in during inference, most of these experts are inactive. In fact, only four experts are active. So they have 32 total experts, out of which only four are active. And for 120 billion, they have 128 total experts, out of which only four are active. That's a pretty small number of experts, right? Usually DeepSeek, they went with this multi-expert architecture where they have huge number of small experts. But here GPT-OSS only has 4 experts. That's pretty small. Now, the reason we have sparsity is that different experts can essentially specialize in different types of questions which have been asked. So instead of just every question going to one big feed forward neural network, based on the type of question, we have specialized experts answering the question, right? So, for example, verbs might go to, let's say, layer one, the the experts in layer one, etc. Whatever. So, essentially, the moment we have experts and the moment we have a routing mechanism which imposes sparsity, it means that every expert is specialized to deal with certain set of questions, and that makes their answers a lot more better. Plus the inference is a lot faster. Rather than having all the parameters active, we can just have a bunch of parameters switched off, like a light bulb goes off and only some parameters which are active. Now that's with the mixture of experts, but we still need to consider how this feed forward architecture itself is designed, right? Now, earlier, before modern LLMs came into the picture, the simple thing was if you had a 2880 dimensional vector, which is the embedding dimension of GPT-OSS, you simply had this hidden layer which has 4 times the number of embedding dimensions, 4 into 2880, and then you had an output layer which has the same dimensions as 2880. That was the simple architecture. But even in Gamma 3 270 million and now GPT OSS, they have implemented this architecture where you have a linear layer, okay? So I'm looking at one expert for now. This architecture will be followed across all the experts, right? So what they do is that you have, let's say, this 2880 dimension, and then you have a linear layer, which means that it projects it into another hidden dimension, which is same as 2880, and then you have an activation function, right? This is one linear layer, which I'm calling L1. They actually have another linear layer, which is L2, where you have the 2880 dimension input. It again goes into a 2880 dimension hidden layer, and you have these outputs. The output is 2880 dimension here, and even here it's 2880, but you have an activation function here. Then what you do is you multiply element wise these two outputs, so that gives a 2880 dimensional vector, and that is then passed through another linear layer with 2880 dimensions, and then you get the output. That's their feed forward neural network, which has been summarized very easily over here. You have one linear layer followed by an activation function. This output is multiplied element wise with the output from another linear layer which does not have an activation function, and then these two output, we have 2880 dimensions here, it goes through another linear layer, right? And that has the output of 2880. That's the neural network architecture here. And usually traditional architectures use the JLU activation function, right? But what they have used is they have used the CLU activation function. So if you compare ReLU, JLU and Swish, so the CLU activation is also the Swish activation function, right? There is actually not too much difference between these two. So the Swish, if you see the green line, it just dips a bit lower than the green, than the orange and the blue line. No one uses ReLU for LLMs, that's out of the picture, but many architectures use JLU, which is the orange line. GPT OSS has started to use Swish. And if you compare the orange line and the green line, there is not too much difference actually, except over here. So I'm not sure why they actually use JLU over Switch. They might have seen performance improvements for sure. Another reason is that the mathematical formula for Swish is slightly simpler than JLU. But there is no one reason why Swish should be used over JLU, because you will see some papers in which Swish performs better. If you see some other papers, you will see JLU performs better. So that is why this is called as Swiglu activation function, which is Swish linear unit, right? So every expert uses a swigglue activation function, and every expert, if you zoom into the expert, it looks something like this. It has a linear layer, a CLU activation, it has another linear layer, and those two are multiplied element wise, and then they go into another linear layer. So you might be thinking, doesn't this increase the number of parameters? Not really, because in the original feed forward neural network, if you take a look at the number of parameters, here the number of parameters are 2880 multiplied by 4 into 2880 in the expansion layer. In the contraction layer, it's again 2880 multiplied by 4 multiplied by 2880. So if you think 2880 to be equal to A, this is 4A square parameters in the expansion layer, 4A square in the contraction layer. So total we have 8A square parameters. Now let's see here. In the first linear layer, it's 2880 going to 2880. That's A square. In the second linear layer, we have 2880 going to 2880. That's A square. And the third linear layer, we have 2880 going to 2880. That's again A square. So it sums up to 3A square. So actually, we have a lesser number of parameters than 8A square. In fact, by almost 3 times. So here the number of parameters increase because of this 4 times 2880. But here we don't have that factor of 4 in these modern architecture. So every expert looks like this. And whenever every token is given for inference, only 4 of such experts are activated. And then their output is pooled together. And the final output which comes out of this layer is still 2880 dimensional itself. Okay, so this is the mixture of experts layer and this is the routing mechanism. The eighth building block which we want to see is the output layer. So if you scroll up and look at the GPT architecture, you'll see that until now, what we have seen is we have completely seen the input block. We have completely seen the input block and we have completely seen the processor block. Now finally we come to output block. When we come to output, there is a RMS normalization, which is the same as this RMS normalization, and there is a linear output layer. What this linear output layer does is that until now we are in the 2880 dimensional space. Linear output layer just projects it to the dimensions of the vocabulary size. And in this case, the vocabulary size is equal to 201088. So this output layer takes us from 2880 dimension. This output layer takes us from 2880 dimension to 201088, which is the vocabulary size. Why this is done is because we want to predict the next token at every stage, right? And I'll explain to you when we see the entire architecture workflow why we need to be in this dimensional space. But remember why we started this whole exercise. The reason we started this whole exercise is we have a bunch of token IDs. If you scroll above, you'll see that when we looked at the input and output pairs, we have a bunch of token IDs which make up our input, right? These ones, these bunch of token IDs, we want to pass through our model and we want to get a prediction. That is what we are seeing right now. So the you take a input IDs, you take a sequence of input IDs, it goes through all these steps. And remember that when you see processor block, there are 24 such processor blocks in the 20 billion architecture and 36 in the 120 billion architecture. So one input sequence like this has to go through a very long journey. It has to first be tokenized, then converted to token embeddings, then go to 24 or 36 such processor blocks, and then come out through the output layer, and then we'll predict the next token. And then we'll need to compare it with the actual ground truth and get the loss. So now let's pay a very careful attention to dimensions. So until now, I have explained to all of you overall how the architecture works, right? But now imagine that you are these bunch of token IDs and let me explain to you with the perspective of dimensions. I always believe that the people who have understood dimensions have truly understood the entire LLM architecture workflow. So if you take a look at these 4 token IDs right now, the first step is they are converted into token embeddings, the higher dimensional vectors which we saw over here. And the embedding dimension is 2880, right? So we have 4 tokens, 1, 2, 3, 4, each of 2880 dimensions. Then we go through the processor block. Let's say the tokens are every effort moves you, whatever, for the sake of simplicity. The first step in the processor block is RMS normalization. In the RMS normalization, we divide by square root of the we divide by the RMS value. Uh, we multiply with scale and then we add a shift. But this operation is per vector level. So the vector dimensions remains unchanged. Also, there is no interaction between one vector and its neighbors. That interactions happen in the attention block. Now, I have mentioned here attention and rope, but there are several key things to note here. Remember that the processor, let's say, has 24 transformer blocks for GPT-OSS, right? So the first transformer block will have full causal attention. The second will have sliding window attention. So we have alternate versions like this. And then attention bias will be there in all the transformer blocks. Along with this, the rotary positional encoding will also be done over here to the query and the key vectors. Remember, we have seen all about this now. We have learned what attention bias is. We have learned what rotary positional encoding is and sliding attention is. We also have learned about grouped query attention. GPT-OSS use 64 heads with the grouped query attention ratio of 8 is to 1. All these things actually happen in this block. And the output dimension is 4096 over here. That's just one dimension which we are using in this case. And the output projection brings it back to a 2880 dimensional space. Now remember, where does this 4096 actually come from? When I explained the attention mechanism to you, I mentioned to you that this D out, right? This output dimension is our choice, that we have chosen to be 4096, similar to GPT OSS. And then there is an output projection layer which projects back the 4096 to the 2880 dimension. And then there is one more RMS normalization over here. So this part right here, which I have shown in green block, corresponds to, if you see the architecture, it's a long way up, but it corresponds to until here. Okay, and then we'll see the rest of the things. So in the rest, so until now we are at, if you check the number of dimensions, we are at 2880 dimensions, right? Then there will be one more RMS normalization, which brings me to which keeps me at 2880 dimension. I still have 4 tokens with 2880 dimensions, and then there is mixture of experts. Now here, although there are multiple experts, my final dimension will still remain 2880. And here we have that neural network architecture which we saw over here, and 4 experts are activated per token. And then we have another RMS normalization, and then we come out of the one transformer block. Then we go to another transformer block. So this is, then we go to TF block 2, then we go to TF block 3, etc. And then after 24 transformer blocks, we truly come out and we go to the output layer, right? Now, when we come to the output layer, we'll first do RMS norm, and then all of my 4 tokens have still the dimension equal to 2880. Now remember, it is at this stage where I want to do my next token prediction task. So I want to convert my dimensions from 2880 to my vocabulary size, which is 201088. So what I will do is that I will take this and multiply it with 2880 multiplied by 201088. So if you take a 2880 multiplied uh, by sorry, if you take a 4 by 2880 matrix and multiply it with 2880 by 201088, the resultant will be of multiplied by vocabulary size, which is 201088. This matrix will be our resultant value. And so let's say now if I have every, or I'll take a look at every token now. So let me take my input sequence here. Let's say this is my input sequence, okay? Yeah, this is my input sequence right here. And now once I've reached my output stage, I have 11, 14. And I have a vector which is equal to the vocabulary size 201088 for all of these. So how am I going to predict the next token now? What I'm going to do is that I'm just going to look at each row and I will apply softmax to all of these, and I will take the token ID with the maximum probability. So if the token ID with the maximum probability might be 55, here it might be 17100, here it might be 2001, and here it might be 1576, right? So this is my LLM prediction right now. And what is the true value? The ground truth is just this input shifted to the right by 1, which might be 11, 15, 14, and 3. Then I will be comparing my uh, true ground truth with my prediction, and then I will be computing a loss function out of this. That will be computed through the categorical cross entropy loss. And that is how one input sequence will be processed. Now, if you want to process an entire batch, you just add the individual losses from the different input sequence, and then you will get the loss for an entire batch of input sequences. That's how one entire forward pass actually happens through the GPT-OSS architecture. I hope all of you have really understood the dimensions over here. Some key dimensions are the dimensions of 2880, which is the embedding dimension. Then the final layer brings it back to vocabulary size, which is 201088. Then we have 8 is to 1 grouped attention ratio here. The transformer blocks will alternate between full attention, full causal attention to sliding window attention. Uh, what else do we have? Attention biases, we have attention sinks. Then the number of experts which are activated for each token, 4 will be activated. The output will be pulled from these 4. So each neural network output is in a 2880 dimensional space. So even if you add the output from 4 neural networks, it will still be in a 2880 dimensional space. And then we get the next token predictions. We have the ground truth. How do we have the ground truth? Well, because in the input and target, if you see, in step number 3, when we created the input and output pairs, we already have the targets, which are the input shifted to the right hand side by 1, right? So this is how we do the forward pass and get the entire loss function through the GPT-OSS architecture. Now I want to take you through code and actually explain to you where all of these things have been written in the code. So there is a folder which is called as architecture. And if you go to gpt-oss.py, here you will see the all the different elements which I just explained to all of you. And this file might seem a bit intimidating right now, but don't be scared by this at all. I'll tell you how to start reading this file. Okay, the key is to start looking at different classes. So if you look at the elements of the architecture, right, if you look at the elements of the architecture, there are classes which are created for every element. So I'll just rub this, and I'll mark in a different color where we see the classes, in a purple color, let's say. So first we get a class for the RMS normalization, and that's this. So I'll mark it with C over here. And the code is exactly similar to the mathematical explanation which we have seen. Okay. Then we have a class for the rotary positional encodings over here. Remember, the query key vectors are rotated by theta. You will see exactly the same description over here for theta and how the query key vectors are rotated. So there is a class for that, which I'm calling it C again over here. Then you have SDPA, which is the sliding window attention, right? You have an attention block over here, which does the query key value computation. Here is where the grouped query attention actually happens. Here is where the rotary embeddings are applied to the query and the key matrices. Then we calculate the attention matrix, and here the grouped query attention, the 8 is to 1 ratio is also applied here itself. Uh, okay, so I hope all of you now can relate the different things which we have learned in the attention mechanism. First is this is where the sliding window is applied to every other layer. If layer idx %2 equal to 0, which means that every alternate layer has sliding window which has been applied to it. These are the sync parameters which are added as columns to my attention matrices. We covered this in the attention bias and the attention sinks section. This is where rope is applied to the query and the key embeddings. So this block is actually extremely important, and we in the theory we spent a lot of time understanding every single aspect which is covered in this block. Remember that there is an RMS normalization before this attention, right? So that is actually included in the attention block class itself. So if you scroll down below, but first let me explain the different class. So this is the attention block class. I'll mark it with a C over here. And then the only thing remaining is this MOE, right? That's basically a class called as MLP block. Here the mixture of experts is implemented. The forward pass through the mixture of experts. You'll see the swigglue activation function which we have covered. Okay. So now you have a class for all of these, right? And then you have a class for this transformer, this entire transformer. There is a separate class for this. So if you see the class for the transformer block, it just has the class for the attention and the MLP. So it has the class for attention and MLP. So you might be thinking, what about the RMS norms and the shortcut connection? Those are actually implemented in the attention in those classes itself. So for example, if you see the attention MLP block, you'll see that the RMS norm is actually implemented here itself. See, RMS norm is implemented, and then x return x plus output. That's the shortcut connection. The shortcut connection I did not explain to you. It essentially makes sure that we don't have the vanishing gradient problem. It gives an alternate path for the gradient to flow. So this has been added here itself. Similarly, if you go to the class for the attention block, you will see that there is x return x plus t. That's the shortcut connection part of it. And then you will also see the RMS norm actually. You will see the RMS norm. So the RMS norm is actually integrated in the class itself. So that's why when you create a class for the transformer block, you just need the attention block class and the MLP block class. That's why they have just two classes here. Yeah, let's see. And then you have what else? That's it actually. That's the whole model which has been assembled, right? You take the input, you convert it into embeddings, you go through all the transformer blocks. Then in the output layer, you have another normalization and the unembedding, which is the output logits, converting it into the vocabulary size, which we saw. So this last matrix, which converts us back into the vocabulary size, which you saw over here, this is also called as unembedding over here in the code. So that is how the architecture file is written for GPT-OSS.py. So if you look at the architecture, you will see the GPT-OSS.py and the Tokenizer.py. And you can even compare the architecture file to GPT-2.py. There are so many advancements compared to GPT-2. GPT-2 did not have rotary positional encodings. It did not have sliding attention. It did not have grouped attention. It did not have attention bias, attention sinks. There are so many new things. It did not have RMS normalization. Many new things have been added as we go from GPT-2 to GPT-OSS. And now the last piece which is involved in the code is the training part itself. So once we have done the entire forward pass, this is where the loss is actually calculated. The loss between the predicted tokens and the ground truth tokens is a categorical cross entropy loss. And once we have the loss, we move towards the training step. This is what we are going to see next. So until now in this lecture, we have finished let's see, we have finished step number 1. We have finished step number 1, 2, 3, step number 4, right? Now we are at step number 5, and we have to then end with step number 6. So let's start looking at step number 5, which is the pre-training pipeline right now. All right, so now we come to the last 2 steps, and then we are almost at the end of the video. So essentially what happens in the pre-training is as follows. Until now, we have seen how to take a batch, it goes through the architecture and we compute the loss, right? Let's say our model has parameters around 50 million, 100 million parameters, and I'll call them P1, P2 up to P100 million. In the next step, what we have to do is that we have to update these parameters. After we compute the loss for every batch, we'll do a simple gradient descent. For demonstration, I'm showing a gradient descent based update where first parameter will be P1 equal to P1 minus alpha times the gradient of loss with respect to P1. Similarly, we'll update these 100 million parameters, right? And this will proceed till the number of iterations for which I want to run my training loop for. That's the simplest version of pre-training. But when we are actually pre-training, and this is one more thing which open source or open weights models don't exactly mention. What's the training optimizer they used? What are the number of epochs, etc. So here what we have done is that we are using an Adam W. We are using an Adam W optimizer, and we are using a learning rate with a warm up and a decay which looks something like this. So that we start uh, in an exploration phase where the learning rate is a bit high, and as we reach a more settled or a good loss function landscape, we go into the exploitation phase. So instead of a constant learning rate, it's good to ramp up the learning rate, stabilize it, and then slightly go on decreasing towards the end. That's the learning rate schedule which we are going to use. Secondly, we are also going to use something which is called as gradient accumulation. And if your context window is large, you definitely need to try this approach. Let's say you want to train with a batch size of 1024. But if your GPU only fits a batch size of 32, then what do you do in that case, right? Uh, if your batch size becoming very large, how do you fit it on one GPU? What you can do is that you can do something with the, like gradient accumulation, and mention gradient accumulation steps as 32. So what happens here is that we will proceed with micro batches. So at one time, only 32 examples will live on your GPU because that's your GPU memory. So we'll compute the loss on 32 examples first, right? We'll compute the gradient. We'll divide it by 32. I'll tell you why we divide by 32. Then we move to micro batch 2. We'll compute the second gradient. Then we'll process micro batch 32. Since there are 1024 examples in one batch, right? And if our micro batch size is 32, we'll need 32 such batches to process 1024 examples. So we'll have 32 gradients at the end of it. And then when we reach the end, we'll add all the gradients and divide by 32. So we'll get an average gradient across all the 1024 batches. That's why we divide by 32 over here. So at each step at one time, there are only 32 gradients which live on our GPU. We don't have 1024 examples which live on our GPU. So you compute the first gradient, you then move to the second gradient in the GPU, you compute it, move to the third gradient. At each computation, you add the first gradient to the second, then third, then fourth, then you add 32 gradients like this, and you take the average value. That's called as gradient accumulation, right? So if the batch size is 1024, but GPU fits only batch size 32, the number of gradient accumulation steps will be 1024 divided by 32. That's going to be 32, right? So whenever your batch size is large and when you're dealing with out of memory issues on your GPU, gradient accumulation is definitely one way in which you can mitigate that. Of course, GPU parallelism, there is this thing of 5D parallelism where you can parallelize on data, model, so many other things. There are many ways to deal with a GPU not fitting or not fitting your model, having out of memory issues, but gradient accumulation is the simplest to explain, and that's what we have done over here. Since we are going to use a small data set and a reduced version of the 20 billion model, we can train on only one A100 GPU. We don't need to assemble a collection of GPUs actually. So the pre-training loop now looks like this, right? For each iteration, we choose the input and output batches. For each iteration, we choose one batch which consists of the input and output pairs. We pass X through the entire model architecture which we just saw. We'll get the logits, which is the output matrix, which was this. Then so this is also called as the logits. We'll compute the loss between logits and the ground truth. We'll compute the loss between logits and the ground truth. We'll back propagate the loss. We'll accumulate gradients till we reach gradient accumulation number of steps. Then we'll update the number of parameters. And remember, since we are using a dynamic learning rate, after each batch is processed, we'll update learning rate as well. This whole thing will continue in a loop. That's my pre-training loop right now. All right. So if you go to the code again, you will see that if you go to training and if you go to trainer.py, here you will see that after we have functions for the cross entropy loss calculation, there is a train model, and here is where we have defined the loop, right? So first, calculate loss batch. This is where we compute the forward pass and get the loss. Then we update the parameters. Then we update the learning rate, etc. That's all actually. And then we are actually saving our results in WandDB. If you're not aware of WandDB, it's essentially weights and biases where you can monitor your training and how it's proceeding, right? So this is the training loop which we have. And take a look at some parameters here. The learning rate which we are using is 3 into 10 raised to minus 4. Maximum iterations, warm-up steps is 100. Minimum learning rate is 3 into 10 raised to minus 5. We need all this because we are using a dynamic learning rate. And we are printing out the loss after every 150 iterations, right? So this is my cosine annealing learning rate. This is what I showed you on the whiteboard, right? This learning rate, this is also called as cosine annealing. Simple way to think of it is exploration and exploitation. That's my cosine annealing learning rate. This is my Adam W optimizer. And I just want to mention the parameters which we have used so that the training proceeds quickly. So we have reduced the number of parameters from what they actually are. So if you look at the GPT-OSS 20 billion architecture, right? They used, if you look at this architecture, they used 64 attention heads. We are going ahead with 8 attention heads. Number of key value heads. So the grouped query attention is 4 is to 1. They used 8 is to 1. Number of experts is 4, whereas they used the number of experts as 32. Then the number of layers, which are the number of transformer blocks, we have varied it, but for here we have varied from 4, 6 and 12, but here the maximum we have tested with is 12. And the embedding dimension, instead of having 2088, they used a dimension of 2880 actually. We used an embedding dimension of 1024. Another thing to mention, which is where parameters are really reduced by a lot, that's the data loader actually. So if you go to the data loading scheme, you'll see the context length which we have used is 4000, whereas they have used a context length of 131000. So these changes give us a lot of reduction in the number of parameters which we have. um, so if you scroll down below, you'll see that we have compared our results with GPT 2 as well, but here I just want to show you the parameters. So the maximum number of parameters which we go up to is around 588 million. Uh, and due to all of the reductions which I mentioned in the attention heads, the number of layers, the hidden dimension, the context window, etc., we are able to reduce from 20 billion to 588 million, but still retaining all the essence, right? So this is for the nano-gpt-oss repository. For the truly open GPT-OSS, here we have also trained an entire 20 billion parameter model, where our model size is actually 20 billion. And here we have trained it with 5 GPUs which are connected together. These are 5 H200 GPUs. So if you want to run the 20 billion model, you cannot do it on one GPU, and you cannot do it on A40. You have to do it on H200. So this nano GPT OSS we did on one A40, that was enough. But for the truly open GPT OSS, we actually did that using the H200 GPU, this one, through run pod. We assembled 5 of these GPUs together and we did distributed training. All of that code for the distributed training is available in the truly open GPT OSS. Now, once you understand how we did the pre-training and the parameter configuration, etc., the last step for us in this lecture is going to be inference, right? So inference essentially is once our model is trained and our parameters are fixed, what happens is that you have the input sequence, right? Input sequence goes through my trained model. I get a new token. That token is assembled to the input sequence, and this augmented thing then again goes to my model. Then I have my token T2 that is up again appended back. Then again it goes to the model. Then I have my new token which is T3. So that's how we can generate inference results. So here I am just showing some inference results which we obtained from our model. If the question was a little, or if the sentence is a little girl went to the woods, our model can produce something like a little girl went to the woods alone. She looked around and the animals had been playing a game, then said, I want to tell you a secret, etc. And if the input is grandmother was telling the kid story about a unicorn, our model can generate text like grandmother was telling kids story about a unicorn who showed compassion when one of them heard the man's sad song. It was a charming idea, etc. So as you can see, we are very successfully able to generate coherent stories using the GPT-OSS architecture. That's incredible to see. If you get this tutorial to run and if you see this on your own, it's a brilliant feeling to replicate an entire architecture fully from scratch. Remember, the model does not know anything about the structure, the form, and meaning of English language, and it learns all of it, and it produces these incredibly beautiful, coherent stories. We also went one step further actually, and we compared GPT-2 and GPT-OSS. So if you see the pink line, that's our model GPT-OSS, and the green line is GPT-2. So we kept these models so that the number of parameters in both of them are roughly equal to 500 million. But due to all the innovations and advancements which we have in GPT OSS, the pink line, if you see, the loss function decreases a lot more faster compared to the blue line. And this was consistently seen. So here you can see we compared GPT OSS and GPT-2, and for all the different configurations which we compared, the GPT OSS loss was considerably lower than even the training as well as the validation loss compared to GPT-2. So in fact, we obtained, so if we had 6 transformer blocks, we have around 13% improvement over GPT-2. If we have 8 transformer blocks, around 6%, and if we had 12 transformer blocks, our we have an improvement of about 30.5%. So that's incredible actually. uh, yeah, and as you can see, the model size was maintained to be roughly the same, so that the parameters are the same and we can have an apples to apples comparison, right? As you can see, inference performance, GPT-2 requires higher end GPU such as H100 or A100. But GPT OSS can be trained on A40 as well. That's one important thing which we discovered. And for inference, we could see that GPT-2 was slightly faster. It was around 30 tokens per second, whereas OSS was slightly slower. Some key insights we have mentioned here are that GPT OSS uses 11% less disk space despite having 4% more parameters. 11% lower RAM usage makes GPT OSS more hardware friendly. OSS has slightly slower inference, and lower memory requirements enable broader hardware compatibility. We even went a step further and actually calculated the creativity score, consistency score, and the grammar score of our generated responses. And we obtained very decent scores across all of these metrics for the GPT OSS architecture. This is the nano-GPT OSS repository, and there is a completely truly open GPT OSS which has 20 billion parameters. And here, the inference results which we have obtained so far are not that great. We have reached this stage where the inference is something like one's down with that and can fund together, etc. But it's getting better and better and better. I'll be sharing both of these repositories with you. Again, this brings us to the end of this video. It's a pretty long video, but now we have built a fully functional GPT OSS from scratch. All the instructions to replicate the repository have been very clearly mentioned on the GitHub portal, but just running this repository is not enough. You can make notes of whatever I have explained to you so that you master these concepts. That's going to be extremely important moving forward. And that's my purpose through all of these videos actually. I hope you understood all the 6 steps: assembling the dataset, data tokenization, creating input output pairs, getting to know the GPT-OSS architecture, rotary positional encodings, grouped query attention, attention bias and sinks, then the sliding window part of the attention, RMS normalization, the harmony tokenizer. So many new things they have added, and I've tried to fit all of that in this video. Then pre-training, of course, we saw the pre-training pipeline and the inference pipeline. And we got decent results with nano-gpt-oss. With the truly open GPT-OSS, we are still yet to get there. But this is one architecture which has 20 billion parameters, and you can run it on your own by assembling 5 H200 GPUs on the run pod. At the end of this video, I want to thank my collaborators who were extremely uh, dedicated and worked on this project: Naman Duvivedi and Aman Murari Singh. I'll mention their information in the description section of this video. Thanks everyone. And the next video in this series is either going to be Nano Kimi from scratch, which is going to be based on the Kimi K2 architecture, or it is going to be Quen model from scratch. So thanks everyone, and I look forward to seeing you in the next lecture. See you. Take care.